Hello and welcome to Tech Simplified TV. Today we have a very special marathon episode based on the topic reliability issues in VLSI. Here we will try to understand how chip fails over time and how engineers try to stop them. We will start our discussion with CMOS reliability issues like TDDB, NBTI and hot carrier injection that slowly weakens transistor and interconnects. Next, we will move to silent killers, electromigration and IR-Drop. Electromigration pushes metal atom and create breaks in interconnects, and IR-Drop reduces voltage and affect the timing. We will see how good layout, current control and temperature management help to prevent all of them. We will also cover ESD, that is electrostatic discharge, where a tiny spark can destroy a whole chip, and the antenna effect, where charge buildup during the fabrication steps damage the gate oxide. Reliability is not just making circuit work, it's about making them last. So, if you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, what is reliability? Next, reliability factors. There are 2 slides on this topic. Next, time-dependent dielectric breakdown, negative bias temperature instability. On NBTI, we have 2 slides. Next, hot carrier injection, soft error. There are 2 slides on this topic. After that, electromigration. Next, self-heating. Next, press migration. After that, CMOS latchup. And finally, electrostatic discharge. All these topics, starting from time-dependent dielectric breakdown or TDDB to electrostatic discharge, these are phenomenon which actually lead to chip failure. So we are done with this slide. Now let's move to the next slide. So we are done with this slide. Now let's move to the next slide. What is reliability? Let's define reliability. Reliability means how likely it is that a product or system or service will work well for a certain amount of time or under specific conditions without any issues. Reliability is related with the performance of a product or system or service. It means when we have a system or product or service, by reliability of that product, we understand that whether it will work properly or not. Properly means for how long it will work and whether it will work under specific conditions without any issues or not. There are few terms are related with reliability, like probability of success. How likely it is work well, that means whether it will be successful in serving its purpose or not. First is probability of success. Next, durability, whether it is durable or not. Dependability, can we depend on its result or its performance? Quality over time. In definition of reliability, always there is a time factor. Availability to do its job. So failure is deviation from compliance with the system specification for a given period of time. We will call a system it's a failure if it failed to perform in a specific way for a period of time. Failure can happen for different types of faults. Reasons might be design bugs, manufacturing defects, or wear out of oxide or interconnect, or external disturbances or internal malhandling of a product. Although not all fault leads to errors. It's not always that any fault is there and it will lead to error. Although sometimes faults lead to errors, and that different kind of failures can happen because of manufacturing defect. While it's getting manufactured, there is a defect. Design bug, was there and it has been overlooked. It was not properly solved before release. And wear out of oxide or interconnect. Instead of our chip, we use 8 to 10 layers of metal interconnect. So wear out of oxide means disconnection of a portion of the circuit or the chip. So it will lead to failure. If gate oxide gone through breakdown, then the circuit will not work properly. So these might be some reasons. A number of physical failure mechanisms that can affect the reliability of a CMOS ASICs. There are some reasons which lead to failure. Now, yield and reliability are 2 most important aspects for development of new technology. A new technology, if its reliability factor is not high, yield is not high. It means if we are manufacturing n number of chip, how many of it coming out good, not rejected? Obviously, when we are manufacturing n numbers of chip, we always want most of them to work. It get used and then it's sold in market and the money get recovered. And reliability, even after selling, whether it's working properly or not. Designing a reliable CMOS chips involve understanding and addressing of potential reasons of failure. We must analyze and understand what could be the potential reasons of failure so that we can give some safeguard. If we overlook all those conditions, there is a huge chance that it will lead to a failure. So here is a table. Failure factor versus failure mechanism. Bulk is a failure factor and mechanisms are crystal defect. Crystal could be defective. There could be crack, surface contamination, surface of the wafer could be contaminated, junction deterioration, impurity precipitation, mask deviation. These are bulk related mechanism. Now comes oxide film. Interface state. Oxide is an insulator. There should not be any free charge. An oxide is a good oxide if it is highly non-conducting. There is no state, free state, no interface state. In practical, it doesn't happen. There are some interface states. Although number of interface states must be within limit. Otherwise, the quality of the oxide film is not considered for a good MOSFET. Interface state, quality of oxide film, time-dependent dielectric breakdown, hot carrier, negative bias temperature instability. These are the issues related to oxide film. Now metallization. After oxide is deposited, then metallization is done. For metal, electromigration, self-heating, stress migration, these are three mechanisms which leads to failure. And environmental, there are some environmental factor also like static electricity, over voltage, surge voltage, latchup, soft error. This static electricity leads to basically ESD, electrostatic discharge. We already have a separate video and article on that. Link is provided in the description. In this discussion also, we will briefly discuss it. So we are done with this slide. Let's move to the next slide. Now reliability factors. What are the factors related to reliability? If a device is under wrong use condition, a failure may occur. Reliability of a device depends on how much stress it can handle. Some factors related to failure are electric load, temperature, humidity, mechanical stress, static electricity, effect of repeated stress. A device not only get damaged because of its manufacturing defect or material defect, it can also get damaged because of handling, rough handling or malhandling. If a device is used under wrong use conditions, a failure may occur. Wrong use condition, wrong handling, these are basically create stress on the product or the device. How much external stress it can handle, that decides whether the device is reliable or not. So some factors related to failure are electric load, temperature, humidity, mechanical stress, static electricity, effect of repeated stress. So electric load. Operation conditions determine life of semiconductor devices. Electric power causes a rise of junction temperature which might lead to device failure. Under which operation condition a device is getting used, that determines life of that device. Electric power can create a rise of junction temperature which might lead to device failure. The electric current should be lowered as far as possible. In most of the electronics devices, electrical limit is mentioned. Voltage and ampere ratings are there. If we do not follow that rating while giving its charge or using it, then device can get damaged. So it's necessary to handle the surge current that flows when the switch is turned on or off and surge voltage of inductive load so that they do not exceed maximum rated values. And many times we have seen in case of home appliances, for sudden surge of electricity in our regular electric line, home appliances get damaged because of this surge of current. For every device there is a rating specified. The surge current is obviously much higher compared to that, and that leads to failure of the device. Temperature. Temperature affects the life of semiconductor products. A rapid or gradual change results in deterioration of characteristics leading to device malfunction. So temperature can affect the device performance and its lifetime. The relation between life L and temperature T is this one. It's an exponential relationship. This is life and this is temperature, absolute temperature. The life will be shortened if temperature rises. A ventilation device or heat radiation device used to avoid overheating issues. Now humidity. Usually IC chips are covered with surface protective film to protect from humidity. If a device is operated under severe humidity condition, it should be operated particularly carefully. Protective film is there to protect the chip, humidity, that is moisture present in the atmosphere. If the operating condition is humid, we must be much more careful about it. We are done with this slide. Now we will move to the next slide. Now reliability factors. There is another slide on that topic. Mechanical stress. If the device is strongly vibrated during transportation or of an extremely strong force is applied to a device during installation, the device may be directly mechanically damaged. In addition, moisture or contaminant may enter the device through the damaged area and may cause deterioration of the device. Now static electricity. Electrostatic charge damage the equipment. Equipment incorporating device is often charged with static electricity. In some cases, and recently, plastic is generally used for casing and structure equipment. Human bodies can also be charged with static electricity. While handling semiconductor devices, it's necessary to take static charge preventive measures. These issues become more serious as device dimensions are aggressively scaled and operating frequencies moving higher. Static electricity is also a damaging thing. It can damage equipment, and human bodies carry static electricity. If we do not handle it properly, it can lead to damage and failure. So we need to take preventive measures. And finally, effect of repeated stress. If a stress is repeatedly applied, it might be stronger than steady stress. A high-low temperature cycle and intermittent internal heat generation cycle can apply stresses repeatedly. The effects of such cycles, such as rearrangement of material structure and fatigue, deterioration of resistance to distortion, are examined and utilized for evaluation of failure. Steadily, a stress is there, and intermittently, a low-valued stress is applied. Continuous application of stress, multiple cycle of stress can lead to failure also. It's not that always strong steady stress will lead to failure. Suppose for a product or a system, high low temperature fluctuation or cycles are there. So that also can lead to failure. So we are done with this slide. We will move to the next slide. Now failure mechanisms. First mechanism is time-dependent dielectric breakdown or TDDB. Gate oxide thickness has reduced with technology nodes. Electric field across T-ox is getting ever stronger. Oxide film breakage is caused by an initial defect, deterioration of the oxide film. So two types of situation may arise. That an initial defect is there in the oxide layer, or deterioration over the time it got deteriorated. Initial defect lead to an early failure. Early failure means process of failure has got initiated from very early use. Now deterioration of the oxide film leads to long-term reliability failure. That is, gradually the oxide film or oxide layer is getting deteriorated and its performance is degraded, and finally reliability failure occurs. Oxide layer breakdown, if applied electric field, exits dielectric breakdown withstand voltage. If we applied for any oxide layer a field which exits breakdown withstand voltage, it will break down. Second point is, even if the electric field with lower value is applied for longer period of time, that may also cause breakage as time elapses. If the electric field has lower value, it's applied for a longer period of time, that also leads to breakage or breakdown of the dielectric layer. This type of breakage is referred to as time-dependent dielectric breakdown. That is, it's not instantaneous, it will take time, and time-dependent. Time is a great factor here. There is an empirical formula which describes the TDDB life, how long it will take. T life in practical use, TT life in test, beta electric field acceleration factor, this beta, and E is electric field strength in practical use, electric field strength in test, activation energy, Boltzmann constant, temperature for actual case. So from this equation we can easily realize that temperature dependency is there and time dependency is there. So TDDB is a time dependent, as the name suggests, it's a time dependent phenomenon. Effective methods to prevent these failures are optimizing the process in order to minimize variability, formation on oxide film with less defects, screening by use of high electric field during inspection or burning, testing showing some trap points are there, and as we know, if close enough, so basically it creates a conduction path through the oxide layer. This is the diagram. We are done with this slide. We will move to the next slide. Now, negative bias temperature instability. There are 2 slides on this topic. To understand it, we need to understand the situation over this region. This is the silicon layer. Silicon dioxide layer is here. And now metal. This is the basic MOS structure. Metal oxide semiconductor. Here we can see some charges are there. We will try to understand the scenario, and then we will come to the physics of NBTI. 4 types of electric charge exist in gate oxide films. We need to know that because these charges play a very important role in this phenomenon. Mobile ionic charge QM, fixed oxide charge, interface trapped charge, and oxide trapped charge. NBTI is an increase in the absolute threshold voltage, a degradation of the mobility, drain current and transconductance of P MOSFETs as either negative VG or elevated temperature. Due to NBTI, there are bunch of parameter value degradation happens of a MOSFET, mobility, drain current, transconductance, threshold voltage. These are some important parameters related to a MOSFET. This bunch of parameters get degraded in case of negative bias temperature instability or NBTI, and it creates an instability. From the name, 3 things we can understand. One is negative bias, temperature, and instability. And for these 2 parameters, this instability basically occurs. So that happens with P-type MOSFET at either negative voltage or elevated temperature. A stronger and faster NBTI effect is produced by their combined action. And in case of stronger and faster NBTI effect, it will happen quickly, and even with great degradation, that will happen if these 2 factors, that is negative bias and temperature, they both of them come into play. So such fields and temperature are typically encountered during burn-in and during routine operation in high performance ICs. During burn-in, that can also happen, and during routine operations of high performance ICs, that can happen. Why it happens? Silicon has 4 valence electrons, that is 1s2, 2s2, 2p4. We know that. At the surface of silicon crystal, atoms are missing and traps are formed. This is the silicon. These valence electrons are shared between 2 silicon atoms. We know that. These positions at surface, atoms are missing, and here traps are formed. Density of these interface states, that is defined by DITUs. When we do the oxidation, most of the interface states are saturated with oxygen atoms. This free, open, and this missing electron missed or trap kind of situation reduced. We tried to show in this diagram. Here 5 atoms, 1 electrons are missing here. Bond with another atoms is missing here. Here oxygen atoms are there. To reduce the number of dangling valence bonds, here dangling bonds are still present. Here after oxidation, number of dangling bonds reduces, still present, quality improves. To reduce the number of dangling valence bonds further, surface is annealed with forming gas. That's a mixture of hydrogen and nitrogen. That hydrogen make a bond with this silicon. These dangling silicon bonds are pacivated by forming silicon-hydrogen bonds. The number of electrically active interface states can be reduced to acceptable range. Now these dangling bonds reduced and it reaches an acceptable range. These silicon-hydrogen bonds have lower binding energy. Elevated temperature and high electric fields break these bonds and interface states reactivated. Their binding energy is low. If temperature is elevated or high electric fields are there, these bonds just break. The exact properties of interface defects, which are trivalent silicon atoms with 1 unpaired valence electron, depends on exact atomic configuration and orientation of the substrate. Holes interact with silicon-hydrogen bond and weaken silicon-hydrogen bond. Now, for a PMOS, at elevated temperature, silicon-hydrogen bonds dissociate. Like silicon-hydrogen, one hole is get associated with that, it becomes positive, becomes a ion, and this bond is broken basically. The effect bias temperature instability can be observed in both P-channel and N-channel MOSFETs. However, P-channel MOSFETs with negative VG stress are more susceptible to this kind of degradation. In a P-type MOSFET, in P-channel MOSFET, holes create the channel when negative bias is applied. Like N-channel device, to create a channel, we need to apply positive voltage at the gate electrode, and for P-channel MOSFET, we need to apply a negative bias to attract the holes. When negative bias is applied, holes are coming close to the interface silicon dioxide interface. There is those dangling bonds and the silicon hydrogen bonds are there. Holes are attracted there. They weaken those interface states, again reactivates. It has been reported for NBTI degradation, channel cold holes are important. As N-channel MOSFET biased into accumulation also has holes at the surface of the substrate, the threshold voltage shift should be similar to P-channel MOSFET. Therefore, the lack of holes cannot be the cause for different degradation behavior. Presence of hole is the creating his situation here. When we are operating N-channel MOSFET in accumulation, we are applying negative bias that accumulates holes near the interface and creates similar situation. The effects on circuits occur primarily in P-channel MOSFET with negative gate voltage bias and is negligible for positive gate voltage. Usually occur because negative gate voltage is required. At gate voltage, if we apply negative voltage, holes are attracted towards the silicon dioxide interface, and here that silicon hydrogen bonds are there, so that bond having lower binding energy, that weakens by hole interface states, they again reactivated. Usually occur during high state of P MOSFET inverter operation. Leads to timing shift, potential circuit failure due to increased spread in signal arrival in logic circuits. Asymmetrical degradation in timing paths can lead to non-functionality of sensitive logic circuit products, field failures. If a circuit cannot match its timing, it's not reliable because a circuit has its purpose. It's designed in that way to match its timing. It cannot do the matching, then it's not working in proper way. So we are done with negative bias temperature instability, and now we will move to the next slide. Hot carrier injection. That is another phenomenon that leads to failure. Hot carrier injection is one of the most significant problems regarding reliability of state-of-art MOSFET. It's an important issue, although in state-of-art MOSFET, that means small dimension or reduced dimension MOSFET, this situation is even worse. It's difficult to reduce the power supply voltage. We are scaling this thing, but power supply voltage scaling, that's a tricky situation. For DSM, that is deep submicron and nano devices, electric field strength is increasing. Devices are getting smaller, and along with that, we cannot scale the supply voltage with same scaling factor, so field is high. Hot carrier is a generic name for high energy hot electrons and holes generated in the transistor. Hot carrier injection into gate oxide film generate the interface state. If hot carrier injected into gate oxide, it generates some interface state in oxide layer. And fixed charge, they do not move, but there are fixed charge, and if number of fixed charge is high, that will lead to deterioration of the dielectric layer condition or its property and lead to failure, breakage and failure. And finally deteriorate the VT and GM, that is transconductance of the MOSFET. As the VT of the FET is increased, the circuit operation will become slow and will finally operate abnormally. VT is high. It will take higher voltage to turn on. It will take more time to turn on. So if it takes more time, the circuit cannot match the final timing. Hot carrier is easily generated when VG is less than VD by 2. That means VD is much much higher than VG. That is, VG is less than half of VD. When VD is much greater than VG, the carrier present in the channel will impact the silicon crystal lattice. From here, if VG is not that prominent, very less, and VD is really high, so electrons which are flowing from here to there, they become highly accelerated. Once they are accelerated, they impact the lattice. Their impact with lattice creates, and more they are going towards drain, the field is higher, so their acceleration increases. Their impact with the lattice, that creates electron hole pair. Here, electron hole pair created. Those electrons are attracted here. If it's impact in oxide, it will move through the gate oxide layer, and the holes are attracted toward base. When VD is greater than VG, the carrier present in the channel will impact the silicon crystal lattice and generate pairs of hot electron and hot hole, that is impact ionization. These pair functions at hot carriers. And now they are working as hot carriers, high energy carriers. Hot carriers under strong VD gain enough energy to break the barrier of silicon dioxide interface and go through the gate oxide into the gate. As a result, either the gate oxide film is charged or the silicon dioxide interface is damaged. These lead to change in transistor characteristic. Hot carriers are generated, and now VD is high enough to break the barrier of this silicon-silicon dioxide interface and go through the gate oxide into the gate. If it overcome this barrier of silicon-silicon dioxide interface and move through this oxide to gate oxide, it's getting gate current, and silicon-silicon dioxide interface is damaged. At device level, the performance get changed. Generation mechanism of hot carrier, there are three types of. One is channel hot electrons, avalanche hot carriers, and substrate hot carriers. Among these three, AHC or avalanche hot carriers, this is most important, create remarkable change when devices are miniaturized. So that is hot carrier injection. Here this SHE, CHE and HC hot carrier injection is shown. We are done with this slide. Now we will move to the next slide. Now soft error. There are two slides on this topic. A very small amount of radioactive elements are present in the package material. We fabricate a chip, we need to properly package it. So in packaging material, a small amount of radioactive element like uranium or thorium, these are present. A small amount. Radioactive material is present, so obviously alpha particles are radiated from it. So abnormal operations of devices is caused by alpha particles radiated from that radioactive element. This problem is referred as soft error. This abnormal operation is temporary, so writing data again can restart normal operation. It's very significant for memory devices. We use memory devices storing data there. So once its data is there and alpha particles change that data, so when we want to retrieve it, that give erroneous result. This problem is more dominant in advanced node devices. In this dimension, the electric charge of signals handled in devices is lowered because device dimension is lower, so operating voltage is also got lowered. Now electric charge of the noise generated by alpha particles that are radiated in the chip has a large impact that cannot be ignored. The operating voltage is less. Now this electric charge of the noise that is generated by alpha particle that become quite significant at this dimension. The alpha particles are generated at the cell capacitor that stores 1 bit data, 1 bit minimum data unit of dynamic RAM. We have mentioned that it's more important for memory devices. The alpha particles generate electron-hole pairs in the substrate. Alpha particles lose their energies in the generating the electron-hole pairs. The electron generated in the process can invert the data of the cell capacitor. The alpha particles has its energy, and that energy creates electron hole pairs in the substrate. In this process, extra electrons are got generated because of these alpha particles. A cell capacitor is considered low if electron exists and considered high if electron do not exist. If it's in high state, and because of alpha particle, these extra electrons are there. So it initially didn't have electrons, so it was in high state. Now electrons are there, so it becomes low state. So state is changed. If electrons are generated in the cell capacitor by alpha particles, data H will be inverted to data L. This is referred to as soft error in the memory cell mode. Soft errors affect memories, registers, and combinational logic also. Memories use error detecting and correcting codes to tolerate soft errors. So these errors rarely turn into failures in a well-designed system. Since we know this error might happen, so there are detecting and correcting codes that's used for memories so that it doesn't lead to failure. We are done with this slide. We will move to the next slide on this topic. The cell capacitor data is read out by bit line by diffusion and then compared with the reference potential. If electrons generated by alpha particles flow into the bit line, the potential of the readout data or reference potential may be lowered. If the data potential is lowered, data will be inverted from high to low. If the reference potential is lowered, the data will be inverted from low to high. So this extra generation of this extra electron and where it's flowing, depending on that, the state is get changed. Because the cell capacitor data is read out by the bit line by diffusion and then compared with the reference potential. It's determined by comparing with the reference potential whether the bit line is at high or low, that is determined. Now, if the generated alpha particles flow into the bit line, so electron is there, so potential of the readout data or reference potential get lowered. Electrons are there. If the data potential is lowered, data will invert it from high to low. If the reference potential is lowered, the data will invert it from low to high because comparison is there. We are doing a comparative study. So the reference potential, if it's get lowered, the data will become higher. This is referred to as soft error in the bit line mode. If the operation cycle or cycle time of the dynamic RAM is shortened, the reference potential will be compared with the data potential more frequently. As a result, soft errors in bit line mode will be increased. On the other hand, change in the cycle time will not affect the soft errors in memory cell mode. So we can handle it this way. Now, prevention of soft error: to use package material that contains less radioactive element, alpha particle generative source. If we use a package material which has less radioactive elements, that will solve the issue. To prevent alpha particle from entering the chip by coating organic material on the chip so that it cannot enter the chip. Improvement of the bit line structure using wire materials of aluminum, polysilicon, etc. Improvement of sense amplifier, adoption of return bit line, etc. There are methods to prevent soft error. We are done on soft error. We will move to the next slide. Now, electromigration. We already have 3 episodes on electromigration. Link is provided in the description. You can watch the video. Here we will briefly discuss about electromigration. While operating, a chip may go above 100 degrees Celsius during practical operation. High frequency power loss and consequent heat dissipation contributes in increased temperature. Rise in temperature enhances solid state metal ion diffusion. Continuous current flow is happening through this interconnect, and when current is flowing, heat is get generated. If proper design considerations are not there, ions in interconnect, they can diffuse. Once they move from their position, that create a void. That means disconnection or open circuit. If connectivity is not there in between conductor, it's open circuit. Either open circuit void situation may happen, and since it's at micro level, they're very close to another interconnect, so it can move from its position and can touch the other. If it touches another interconnect, then it's creating short circuit. So electromigration is caused by scattering of moving electrons with the ions by momentum transfer between electrons and ions in metal interconnect. This ion-electron interaction is sometimes referred to as electron wind. This causes wire to break or to short circuit to another wire, just what I have discussed. Such situation, void in interconnects, can lead to open circuit, that is chip failure. EM is one of the most menacing and persistent threat to interconnect reliability. Mean time to failure due to electromigration, that is MTFF, this is the expression. It means mean time to failure, constant of wear, current density. MTFF is proportional to current density, and the following factors can reduce the failures caused by electromigration: crystal structure, grain diameter, crystal orientation, addition of another elements to metal film, laminated wiring structure. These are usually followed to prevent from electromigration. Now, electromigration depends on the current density J. It's more likely to occur for wires carrying a DC current where the electron wind blows in a constant direction than for those with bidirectional currents. So, wires carrying DC current or one directional current, electromigration is predominant thing, and we need to consider some design specification to get rid of electromigration or EM. We are done with this slide. We will move to the next slide. Now, self-heating. Bidirectional wires are less prone to electromigration, although their current density contributes in by self-heating. High current dissipate power in the wire. If high current is flowing, it creates heat. Since surrounding oxide or low K dielectric is thermal insulator, the wire temperature can become significantly greater than the underlying substrate. So, around interconnect, there are low K dielectric. Dielectrics are electrical insulator and they are thermal insulator also. So, they do not carry away that heat. Continuously, heat gets generated and that cannot get dissipated. So, hot wire exhibit greater resistance and delay. We know that property. Electromigration is also highly sensitive to temperature. So, self-heating may cause temperature-induced electromigration problems in the bidirectional wires. Electromigration is sensitive to temperature. We have seen that equation. So here, if continuously temperature increases, it can lead to temperature induced electromigration also. So brief pulses of high peak currents may even melt the interconnect. Since brief pulses of high peak current create huge temperature that might melt the interconnect. A significant percentage of device self-heat energy flows vertically and laterally to the interconnect layer. The local temperature rise depends upon thermal dissipation dissipation paths away from the heat energy originating element. Self-heating is dependent on the root mean square current density. So, depend on current density. Self-heating is also dependent on IRMS. Temperature of any point in the chip depends how far from the heat generating point or heat generating element. Depend on that. A conservative rule to control reliability problems with self-heating is to keep JRMS 15 milliampere by Rm square for bidirectional aluminum wires on silicon substrate. So the maximum capacitance of wire can be estimated based on the IRMS current. Current must be at lower side. There is a calculation and we must follow that. Electromigration from high DC current densities is primarily a problem in power and ground lines. Self-heating limits the RMS current density in bidirectional signal line. So this is self-heating effect. Self-heating effect can also lead to electromigration and failure. So we are done with self-heating effect and we will move to the next mechanism. Stress migration. Stress migration is another failure mechanism. Stress migration or stress-induced voiding is wear-out failure mechanisms in chip metallization. It causes an open circuit in the metal interconnects, especially at the via, since it is the weakest link. Stress migration is caused by interaction between thermomechanical stress in interconnect system and the diffusion of vacancies. During fabrication, we fabricate layers after layer. The whole process need to go through many thermal cycles. For these steps, once temperature is at high level, then again cool down, then again high level. So metals, not only single metal layer, there are multiple metal layers. So metals basically, those metal layers goes to high temperature and again cool down. Although there are different types of materials, how they behave under temperature or thermal cycle, how they expand, how they relaxes, that is not identical because materials are different. There is this thermal coefficient is different. This thermal expansion of metal and dielectric, these are completely different. So the existence of thermal stress in the interconnect is caused by thermal expansion mismatch between the metal and the surrounding materials. Surrounding materials like there are oxide layers, there diffusion barriers, silicon substrate, all different things are there. The BOL interconnect structure consists of several different materials like metal, dielectric, diffusion barrier, silicon substrate and capping layer. Fabrication of the structure involves several thermal cycles from room temperature to above 400 degrees centigrade. A large amount of stress can be introduced due to thermal expansion mismatch among these materials. Now, metal expands due to heating and then contracts during cooling process, although unable to retract to the original since the metal is constrained by the other material. As a result, there is a tensile stress in metal layer. Now, metal atoms moves to balance stress condition, thus void is created. Now this metal when cool down after high thermal cycles, they don't get back to its original situation because now metal is surrounded by other materials also. So there is a tensile stress created in the metal layer. Now metal atoms move to balanced stress condition. Thus void is created. Now void in metallization tends to nucleate and grow around the vias and block the flow of electrical current due to open circuit condition. Void diffusion is shown here. The void is moving here and continuously void this creates, they nucleated, they create a bigger void. Void creation just below the via, that means current cannot flow here. This is a void area. There is disconnection, that is open circuit. So it's creating an open circuit condition and current will not flow. If current is not flowing from there, so its circuit is not working in proper way, it lead to failure. Now this is stress migration. We are done with this slide. We will move to the next slide. Now CMOS latchup. CMOS latchup is also another failure reason. We have a detailed episode on CMOS latchup. We have an article on that also. Both the link is provided in the description. You can watch the detailed episode and read the article. Latchup is a destructive short circuit phenomena, the CMOS structure. It can be defined as a low resistance path between voltage levels. It caused by low impedance path between power supply, rails of MOSFET circuit through PNP and parasitic structure underneath. need. The structure is here an N plus zone, then this P substrate, then here N well, that is NPN, and in this way also P plus zone, N well, and here it's P. So PNPN structure is getting here. Two back-to-back transistor is forming a PNPN structure. N, P, N and P. The circuit function is disrupted by latch-up and currents are frequently large enough to cause permanent damage. The parasitic PNPN structure resembles an equivalent to silicon control rectifier structure. And we know in silicon control rectifier or SCR, is sudden huge current flows. This is the characteristics, IV characteristic of SCR. So a PNPN structure which created by PNP and an NPN transistor stacked next to each other. Immediately after latch-up trigger, one of the transistors starts conducting and the other one begins to follow it by start conducting. They both stay in saturation for as long as the structure is forward biased and some current flows through it. This is not the desired path of flow of current, although this parasitic PNPN structure huge current flows and this can lead to CMOS failure. We are done with this slide. We will move to the next slide. Now, electrostatic discharge. ESD is the release of stored static electricity. The most famous ESD in large scale is lightning. ESD event that take place in chip is not visible. ESD destroys about 20% of electronic components before they are installed into a system. Even before installing in a system, that is destroyed by ESD. ESD may only damage a component, but it leads to further subsequent damages within brief time during circuit operation. If a component is damaged, again its performance gets subsequent damages within brief time during a circuit operation. So a person can acquire charges by simply walking across a room. When such a charged person or object then approaches an IC, an ESD event occurs, characterized by high current within few nanoseconds. A high current density and or electric field can damage conductor, semiconductor and insulator in an IC. High current within very short period of time, few nanoseconds, can damage an IC. Electrostatic straps are used in industry to protect from ESD where electronic circuits are packaged and assembled. The circuit present inside the IC will tend to be partially damaged or might break down when this high voltage pulse enters. When we buy different semiconductor components for computers, we get it in a dark gray package. We all have seen that. That is external protection for ESD event. ESD in an IC is usually start with oxide breakdown which result in percussion path. The high current density damages the semiconductor devices through thin film, fusing, filamentation and junction spike. The high electric field on the other hand can cause failure through dielectric breakdown or charge injection. So ESD is a very prominent condition where a device might lead to damage. Within a very short period of time, huge current flows. So we are done with electrostatic discharge and actually we are done with today's discussion. Today we have discussed about different reasons which may lead to the failure. So we are done with today's episode.
Today we are going to discuss about electromigration in analog and digital designs. So what is electromigration? Let's see. Electromigration or EM is a aging cum failure mechanism associated with the average and RMS current densities in metal or via interconnects. EM analysis is performed on cell external interconnects as signal and power nets. EM goes in a very positive feedback loop with temperature Joule heating. If left undetected, it can lead to performance degradation and finally chip failure over time. So let's see the physics happening in electromigration. A phenomena of molecular rearrangement happens in the solid phase caused by electromagnetic field. In addition, when current density gets too high, the momentum transfer from electrons start to happen. This result collision, which causes drift of metal ions from their original position, depends on conductor, crystal size, magnitude of forces, temperature, and mechanical stress. So, we have just talked about what EM is and what the physics happening. Now let's see in VLSI how the damages are caused. In this photo, we can see a void is getting created in metal via metal connection. So here we can see this will cause a open circuit in long run. Here in a single metal wire, we can see it is causing the open circuit failure. Here we can see hillocks are getting created and they will finally join the two parallel metal lines, causing short circuit failure. So we just have seen that what is the physics and what the damage causes. But when we design any circuit in VLSI, we have to predict these things in advance so that the circuit don't go and damage over time. So for this, we have some predictability. This predictability comes from Black's equation. So Black's equation is a mathematical model for calculation of mean time to failure of any semiconductor circuit under the influence of electromigration. So this is the mathematical form we can see in the screen, and these are the components of that equation. This Black's equation is used to predict the mean time to failure for electromigration. Here, another important point, there is a basic thing, it's called bleach length. What is this? Anywhere that has a length below this threshold length will not fail by the electromigration. So, if any metal strip or any via is less than the bleach length, it will not harmed by the electromigration. Let's see how EM damages a metal or a via. What happened inside? First, the Joule heating I square R caused by the currents in metal interconnects. If this heat is low, heat gets dissipated through the metal interconnects. If this is high, void or extrusion get generated in metal interconnects or vias. Void or extrusion narrows the metal route. This in turn increases the resistance. This again increases the heating effect. So, it acts in a very cumulative positive feedback and it goes on increasing. So one is increasing another and finally the damage happens. So here let's see the pictorially what happens. First, increase of the local current density. This causes increasing in Joule heating. This in turn increase the temperature. This starts the growth of void or extrusion. Now, these last two steps marked by red arrows keep on going in a positive feedback loop, and finally, whatever was getting created, void or extrusion, that finally causes a disconnect or a short circuit, and the circuit performance is damaged. And in between stage, the performance is getting slowly degraded. Now, let's come to the method of EM detection. In VLSI design, we have to detect the EM in very advanced in the design stage. There are two different methodologies are there. One is for the analog or the semi-custom and second is for the digital. The EM analysis, the physics behind is same, but when we predict it during our designing process, we have to follow different methodology for the prediction or the violation detection. Before we go in detail of each of them, let's see in a general bird's eye view what is a circuit and how it is detected. The violations mean the EM violations. So a circuit we can imagine as a interconnection of different cells by different nets. So nets are shown in purple color. Here you can see, here the purple color, these are the nets, and sky blue color, these are the cells. So generally the nets are extracted in SPAF format and the cells are extracted in DSPF format. So these are parasitic extraction. Later I will exemplify the SPAF and the DSPF. These are one of the prerequisites that we need to do. So both type of analysis is done. One is at the interconnect level and as well as the cell level, because inside a cell there will be some metal wires and they can contribute to a EM violation. So we have to do both. What inputs are required? Number one is RC parasitic, SPAF for DSPF. These are two different formats. I will differentiate them at later stage of this video. Cell or net specific data. These will I also share what the data is, and technology specific EM rules from the foundry. Okay, this third point is very much important. This rule actually gives the capping level after which a metal doesn't show the current, the RMS current or the peak current, whatever the current we are seeing in a net. This threshold, if not crossed, it doesn't show the violation. But if this threshold is crossed for any of the net, metal, via whatever, that will be predicted as a potential EM violation. Now I just give the overall bird's eye view of what things are needed and how we analyze in nets as well as cells. So now let's jump into the analog or full or semi-custom designs. Let's describe first the flow and let's see where the EM stands in this entire flow. So design specification, then comes the schematic design, then the basic circuit simulation is a functional simulation, then the floor planning or partitioning, then placement and custom routing, then layout generation or changes, then we do the DRC and LVS, then we extract the parasitics, also abbreviated as PEX. Then in the next stage, we do the EM and IR analysis. Now, a violation is there. Yes. So we get the violation map and we go back to the layout, overlay it and see the different hotspots and we do the necessary changes. If there is no violation, then we proceed towards the next steps. So from layout generation or changes till the EM analysis, it happens in a loop until all the violations are cleared. This is overall picture or the bird's eye view at what stage we analyze or predict the EM and what things happen for a designer. Now let's see what things we do and the nature of the analysis. In analog designs, EM has a unique flavor because currents in analog circuit vary from design to design. Yes. So if your design is a PLL, it will be different. If your design is a band gap, it will be different. If it's a DC-DC, it will be different. So each design, the analog circuit currents, the levels of current, I mean to say, will be different. It can vary from nanoamps to a few amps. Amps means where we are dealing with the power circuitry, high power applications we are using. In analog circuit, it is important to note power rail, VDD, VSS and signal interconnects carry currents nearly the same order. So power nets and the signal nets have more or less same amount of current. Total number of nets pretty less than a digital design because analog semi or full custom design are handcrafted and so the designs will have less number of nets overall. In analog designs, say whether it is a full custom, semi-custom, in any case, we extract a DSPF netlist from the layout which includes R, C, CC plus the tail comments. This is a very important point, the tail comment and also the LVS log. This netlist is then used to simulate the currents in the power nets as well as interconnects, signal interconnects. As I mentioned earlier, if any of these resulting currents densities exceed the EM safe boundary, a violation is flagged for that particular net and a violation map is generated. So this could be GDS, RV, whatever, and we overlay this violation map, the hotspot map over the actual layout and we point out the faulty points. So this was for the analog designs. Now let's come to the digital designs, generally the SOC or ASIC, whatever we call, how EM is done here. Before jumping to the details of the EM methodology, let's see the flow and where the EM is standing. At what stage we do the EM analysis to predict the potential threats. So first the design specification, then RTL coding, then verification, this is a functional verification, then synthesis, then the power routing, global placement, detailed placement, clock tree synthesis, then global and detailed routing, then layout generation and changes, then DRC and LVS, then the parasitic extraction, then EM and IR analysis comes. So at this stage, the EM and IR analysis is done. If a violation is reported, yes, so we go back to layout generation or changes. This continues until all the violations are corrected. Once there is no violation, we go towards the next steps. Now let's see in a digital design what are the important points for a EM analysis. Unlike the analog design, the power rails VDD VSS in a digital circuit carry DC current of nearly fixed magnitude. And this is the most important point in a digital design. Clock and signal interconnects carry AC currents. AC mean to say like pulse or PWL. Hence, the current changes direction with respect to frequency. In a digital design, generally it's a huge as compared to analog design and massive amount of clock and signal interconnects connecting a sea of logic gates. So here count of nets is huge. So first, the EM critical nets are filtered out. So this is the methodology inside the tools and it's their proprietary thing. Then the SPEF is extracted from the layout, including R, C, CC plus tail comment. The tail comment is the most important thing that must be there, extracted for these EM critical nets. Then SPICE simulations are performed on these nets to get the currents, that is average current, RMS current, peak current, whatever we are having. Now we have the EM thresholds from foundry, and if any of the resulting currents or the current densities exceed the EM safe boundary, a violation is flagged for that particular net and a total violation map is generated. Then this violation is overlaid onto the actual GDS and hotspots are identified and corrected. Now let's talk about the EM detection fundamentals. So we have seen both analog and digital. Now we are doing the crux of the analysis. So what inputs we require? Parasitic, netlist, SPEF or DSPF, test vector based on the functionality, SPICE model, SPICE options. Because to generate the currents, we have to do the SPICE simulation, the average, RMS, peak, this kind of currents. These are combined into a SPICE deck. Then transistor level SPICE simulation happens. In analog, we know that we do the SPICE simulation, and in digital, we have just discussed that for EM critical nets, we do these things. This results peak RMS or average current. The worst current of each resistor is compared with the EM threshold, and this threshold comes from the DRM. As a result, we generate the violation map. The metal or via which are having higher current than the allowable boundary limit as per the DRM are flagged as violations. So it could be current or it could be current density, both. We just discussed the general methodology, and now let's look into the SPEF and DSPF, the similarities and the dissimilarities. So here is a short snippet of a SPEF. A SPEF contains a header section, then a name map section. So these nets are numbers, and these you can see the hierarchies are also here. There will be a port section. Ports means the ports of the design. Layer map will be there. This layer map comes from the technology also, because each layer in your layout will have a number, and correspondingly it will have a layer name. So like 21 is metal 1, 22 is via, and 23 is metal 2. Then for each net, each particular net, there will be a DNet section. So if we see DNet, here number 5 is there, and this corresponds to net 1 from the name map. So the details of this net, including the parasitics, will be there. And in the resistor section, we'll see this red color tail comment. It will contain width, length and LVL. LVL means this is the layer map layer number. So 23 here means metal 2. In case of via, instead of width and length, there will be area reported. The LVL will be still there. So this is just a snippet of SPEF. How does it look with the tail comment? Here, the snippet of a DSPF is shown. It will also contain a header section. The difference between the SPEF and DSPF is the DSPF is a ready for SPICE simulation. So there will be a sub-circuit definition. There will be a net section. So this net section, the nets are described like ground net. It will have its parasitics here. The resistor is having the tail comment. Other nets are also there. So I have just given a snippet, and here there will be the tail comments also, another net. And finally, there will be an instance section. So this is used in a SPICE simulation directly. So here the SPICE instances of the different internal parts will be there, and there is a .ends at the end. So this ends the SPICE sub-circuit. This is for a buffer, right? So sub-circuit buffer ends here. This is how DSPF is different, because in SPEF there will be no instance section. In DSPF it will be there. A DSPF is a SPICE ready format, while the SPEF is not a SPICE ready format. Now we have discussed the EM, its physics, its detection methodology in both analog and digital. Now comes the mitigation part. Now mitigation part is same in either of the cases, because we have to make the changes in the layout. We have to avoid 90-degree corners on high current nets, even distribution of multiple vias. We have to avoid abrupt wear width reduction. We have to double or multiple vias have to be used instead of single via which are getting violated. Length shortening of a metal or a via below the bleach length. Increase the wear width to reduce the EM. avoid using the parasitic extraction RSPF. This is a reduced format. So we have to avoid this at all cost. We must use DSPF or SPF with tail comments. So here, after the violation are detected, we have given the scenario how the violations are mitigated. This is not only the exhaustive list. As per technological progress, we have different more scenarios, and we act according to case by case basis. Hey guys, welcome to the 20th episode of Q&A. Viewer Satyanshu Prakash has asked in the episode of Electromigration Analysis in Analog and Digital VLSI Designs, can you please explain if the EM get affected with temperature, voltage and frequency? Today, we will be focusing on the impact of various heating effects inside the chip and how EM is impacted according to them. So, sit tight and enjoy the learning experience. Hey folks, welcome back to the computer screen. Today we are discussing the question from Satyanshu Prakash, where he has asked to explain the details of effect of temperature, voltage and frequency on the electromigration. He has asked in the comment section of the video Electromigration in Analog and Digital Designs. Today we will be focusing on the effect of temperature on electromigration, and we will cover the rest of the parts in upcoming episodes. So in today's episode, we will be covering these topics. First, introduction. Next, we will revisit the Black's equation. We will discuss Black's equation interpretation in EM in VLSI. We will also do the graphical tour of the temperature versus mean time failure, that is MTF. Next, we will look into the temperatures, all of which coexist inside the chip. Next, we will consider all the heating effects inside the chip. Finally, we will summarize the entire discussed topics. So, here is the menu for today. Without any further delay, let's begin. Introduction. So, this particular introduction will be useful for those who haven't also watched that particular episode in which the question was asked by Satyanshu. You can go ahead, watch this episode, and then you can go back to that particular episode. There is no issue. Many of the IC failure reasoning either thermally activated or related. The IC failures are maximum impacted by the thermal reasons. Hence, predictive analysis is much more important in VLSI reliability analysis. Just to support the first point, I would like to emphasize here, you might have seen that in our CPU, we have a fan over it and we use the heating paste. Also in normal PCBs, if we have a IC which have a heatsink, we attach an aluminum piece to it to dissipate the heat. And also we use a thermal paste inside for the good conduction. All these observations you can have from your day-to-day life, and you can now focus on to the actual VLSI reliability analysis, because at the end it is made on silicon and the heat has to be tackled, and that heat is a much more damaging factor than anything else. In VLSI we use the predictive analysis. Predictive means we use mathematical models inside the simulator, and hence we predict that how long this particular chip will run before fail completely or before a significant damage is there. This is the importance of the predictive analysis. And when we do this predictive analysis in the physical verification stage, we take the help of the tools. Those are able to judge the long-term effect coming out of electromigration and can detect which and where all these failures may come. Accordingly, we take corrective actions so that we can mitigate the effects. Let's move on to the next point. There are various temperature generation mechanisms in modern ICs. When you see that a IC particularly getting heated, you may think, okay, it is getting heated, but that heat, if we split into components, it is contributed by multiple reasons. The heats are coming from multiple sources. Inside the chip, not outside the chip, inside the chip. And the temperature which is there in the ambience where the chip is operating, right? That temperature is already there. We are not talking about this. That particular ambient heat will be there. In addition, inside the chip, multiple heat sources are there. We will discuss today all of this. We are just having the introduction right now. A chip may go above 100 degrees Celsius during its practical operation. That's a very important point because in advanced CPU casings, sometimes there are different kind of coolants are also used. Why all those coolants are used? Because the temperature goes high, you have to cool it down. If you do not cool it down, the thing will get damaged. Whether it is a CPU, whether it is a GPU, all these things. You will see there are metal fins on which we have used fans. We use more than one fan in the CPU box inside which we keep the entire motherboard and all the stuffs. However, in the design level, we must take precautions that maximum extent we can prevent all these heatings. Rise in the temperature enhances solid-state metal ion diffusion. Since the diffusion coefficient in solids is much smaller than liquids, electromigration in solids occur at much slower rate. This is a very important factor because the diffusion in liquid happens faster, in solid it happens slow, and hence it happens slowly but gradually but continuously over the time. Since it is kind of relevant to the human ages when we run for a long time and we become old, that similar concept is coming here, and that's why we call it aging. The aging of the silicon chip, where the functioning degrades to some predefined values. Electromigration is caused by scattering of the moving electrons with the ions, that is, by momentum transfer between electrons and ions. This is a very simplistic way we have explained what happens inside the electromigration phenomenon by the physics. This ion-electron interaction, sometimes referred to as the electron wind. Someone say it is ion-electron interaction, someone might say electron wind. So you may find different terminology. So I have kept all these things so that you have a proper pointer here. So you can go in any direction, or whenever you are reading any particular article, you will be able to interpret what it is meaning. So we are done with this particular slide. Let's move on. Black's equation. This equation is very important equation. I have explained it in the main episode on which the question was asked. However, I am repeating the equation here because it has a very much important significance. That's why you will come to know. Black's equation is a mathematical model for the calculation of mean time failure, that is MTF, for a semiconductor circuit in VLSI which is under influence of electromigration. And one thing I would like to clarify, electromigration is not only for the VLSI thing, it happens, it's a basic physics. However, since we are focusing on the VLSI electromigration, we are focusing much more on the things that happen in the VLSI. So here is the equation of the mean time failure. You can see, let me bring my mouse. Here you can see the T factor, that the temperature in Kelvin. This equation you can see at left hand side as Y we have MTF, X is here which is T. So it's simplified way we can say that this is e to the power 1 by x, and if we plot a simple x versus e to the power 1 by x here in a normal graph, this kind of graph will show up. So I have kept only the positive axes. I have not gone in other axes. This is the plus x and plus y axis. So here goes our x and here goes our e to the power 1 by x. So this will be a kind of mathematical representation in the graph. So you can have an idea that how this equation can have a representation. Later we will show how actually this MTF is plotted in graph. Don't worry. So the components in this particular equation are: A is the cross-section area dependent constant, J is the current density, T is the Boltzmann constant, T is the temperature in Kelvin, N is the model parameter. All these things are there. I have highlighted this T with a different color because today in this episode we are focusing on temperature, that is the heating effect here. Hence our focus will be entirely on the T part today. So I have explained the significance of the Black's equation in today's episode as well as in the electromigration. So one more thing here is Q is the activation energy. So we are done with this particular slide. So let's move on to the next slide. Black's equation interpretation in EM or VLSI. Probability of failure is termed as the failure fraction. Now, these are mathematical terms that correlates the mean time failure and how the industry expects all the failures. So in this slide, we will be focusing on these terminologies which are used to judge the failure and represent the failure. And that's how the VLSI industry categorizes and depicts the failure. Industrial markets demand low failure rate expressed as defective parts per million, abbreviated as DTPM, over the entire chip lifetime. Few slides back I have just talked about the aging. So here you can see the chip lifetime. Both are synonymous. VLSI reliability engineers translate this chip level specification to specific fail fraction targets in units of failure in times, that is FIT, on individual resistors. So these things lay well inside your simulator. These are calculated, and sometimes in the figure of merit of any silicon chip, all these factors may come. The classic Black's equation relates a mean time failure. Now you can correlate all the terminologies that I have just depicted in this particular slide. Failure fraction, DPPM, FIT, and now MTF. So all these are correlated. In Black's equation, T corresponds to the contribution from the ambient temperature as well as current induced temperature rise due to the Joule heating. So don't worry, we'll talk about all other components, but for now you can just bank upon that the T corresponds to the ambient temperature as well as the rise in the Joule heating. These two components are for sure there, contributes to T. There are other components come later. Temperature versus MTF. Here in this particular slide, we will be not plotting but kind of visualization. This is the x-axis, which is time. Y-axis is the temperature. So this is a rough idea just for things to get into your mind. Now this green dot represents the MTF. So you can see if the temperature is low, lifetime is large here. As the temperature go high, so you can see the mean time failure point shifts left side and the time span is much less than the previous one. In the similar way, if we go higher in the temperature, the point comes closer in the timeline. And we go and much more higher, the point comes closer. That means with higher temperature, we have a less lifetime of a chip. That means a faster aging. So this is the purpose of this particular graphical representation. So generally we have time here, it is long, so the life is long of this particular chip. And for this particular chip, where the temperature is going really high, the lifespan is much less than this one. So this way you can visualize how the temperature impacts the aging. And behind this, only we have taken consideration of the electromigration. You can recall the Black's equation, you can recall the e to the power 1 by x graph I have just shown you sometimes back. And now I will show you the graph that is used in the industry. This is the graph. Let me point with the mouse. So here we can see the delta T, and here is the ratio, that is MTF by MTF of 300K plus delta T. So this way the industry plots the graph, and don't get confused, this is a logarithmic scale. Okay, so this one is a logarithmic scale, and here is the delta T. So this way in the silicon chip, the MTF is plotted with the delta T. So folks, we are done with this particular slide. So let's move on. Temperatures coexist inside the chip. So far, we have discussed about the Black's equation, the different terminologies those are used to represent the lifetime in the figure of merit, how different companies will exchange data about the lifetime, which all leading to the electromigration, right? Now, we will see the effect of multiple temperatures on the electromigration. Before that, let us take a tour of all what type of sources of the heat inside the chip. First, the metal interconnect Joule heating. So it could be metal, it could be via anything. So Joule heating, we already know that causes the heating, which is a kind of primary reasoning for the electromigration. Next, we have the ambient heat inside the chip. This is obvious. The chip has to operate in ambience. Next is the SOI self-heating. You must know that UT-SOI CMOS are nowadays a lot of popular because of low leakage factor. However, SOI increases the self-heating. It's a huge effect, and I think in many simulators, this self-heating effect is nowadays also getting considered for the EM. And one more thing, the FinFET and gate-all-around devices, some of them are bulk. However, many of them are SOI devices. Whether it is a CMOS, basic CMOS, or the FinFET or the gate-all-around, the SOI impact of the self-heating is there. Nowadays, we also focus for the EM violation. We consider the self-heating effect. Next, high frequency switching operation released heat. So generally we are talking about the electromigration, and nowadays the circuits which we use in our day-to-day operation operate at very high frequency, maybe in the gigahertz rate. or it may be higher. All those high frequency switching operation, you can visualize when it is switching, right? The current is moving to and fro in the metal or the via, and that movement is causing a lot of heat because electrons are moving in opposite direction with the change of the polarity during the switching operation. All those things goes to the basic physics. I think you already know it. Now, all these heating effects are considered together, and we can think that all those are contributing to the T. Here you can see the T. This temperature is the final product of all these heat source that just been explained in this particular slide. So we are done with this particular slide. Let's move on. Heating effects inside the chip. Now we'll discuss about the effects of all these heat sources one by one. Designs at below 10 nanometer node are typically based on FinFETs and gate-all-around FETs. I just mentioned about this even I think in the last slide. FinFET and gate-all-around devices also suffer from significant self-heating effects. As I mentioned, these FinFETs, most of them, and the gate-all-around may be on the SOI devices to reduce the leakage, and hence the self-heating effect coming into the play. One more thing I'd like to mention, because the buried oxide layer, the heat cannot dissipate, but for bulk, it can dissipate through the substrate zone. However, for buried oxide layer, if it is there for the SOI devices, the heat cannot go out. So the heat whichever getting generated stays within the chip. That is the self-heating. The high transistor density gives rise in the high heat flux inside the chip. So this is another cumulative effect which we have. Inside the chip, there will be millions of gates, right? So there we have multiples of those millions as the basic transistors. Those all transistors are contributing to the heat, and adding up the total heat inside the chip, the packaged chip goes high. In addition, inefficient heat removal paths give rise to the thermal ambient. I would like to mention one thing here. The chip may have or may not have a heatsink or the filaments that we see usually outside the CPU or something like that. However, the fact is that whatever is getting conducted out of there may not be well connected to all of the path where it is generating the heat. So this is the main theme of this particular line. The thermal conductivity in the confined region of the silicon fin is degraded due to lattice vibrations, that is phonons, plus the addition buried oxide layer in the SOI FinFETs or the oxide that surrounds the nanowires in GAFETs. So here another physics has been touched base because of the lattice vibration. It also generates some energy, right? And some of that energy could get converted to the heat, and which will finally contribute to the temperature. So this phonon vibration can directly or indirectly contribute to the heating effect. You have now a picture in your mind of all the things that is getting the heats generated inside the chip. Let's move on to the next slide. Let us summarize all the things we have discussed so far. All active and passive components and the wire interconnect dissipate heat during the circuit operation. Even in silicon, sometimes we create both kind of devices. High frequency power loss and consequent heat dissipation contributes in increased temperature. This situation is further worsened with addition of high ambient temperatures. All of these above mentioned temperatures reinforce EM by contribution of thermal energy towards the electron wind. This is a very important point of this episode, right? All the heating effects we have talked about, all those temperatures reinforce the EM by throwing energy towards the electron wind. Rise in the temperature enhances solid state metal ion diffusion, which is in turn enhances electromigration effect. Combination of high heat flux and or high current densities driven in the advanced designs, EM can cause more damage in lower metal layers. So folks, with this particular slide and all these points I have discussed throughout this particular episode, things might have cleared in your mind with respect to the physics point of view, that what is the effect of temperature on the electromigration and hence the aging of the chip. So we are done with this particular slide. Let's move on. Hey guys, welcome to the 21st episode of Q&A. Viewer Satyanshu Prakash has asked in the episode of Electromigration Analysis in Analog and Digital VLSI Designs, can you please explain how the EM get affected with temperature, voltage and frequency? In last episode, we have already covered the effect of the temperature on electromigration. Today, we will be focusing on the effect of voltage and frequency on electromigration. So sit tight and enjoy the learning experience. Hey guys, welcome back to the computer screen. In today's episode, we will be discussing about your Satyanshu Prakash's question to explain the effect of temperature, voltage and frequency on electromigration, which he has asked in the episode of Electromigration in Analog and Digital Designs in this particular channel. In the last episode, we have discussed about the effect of temperature on electromigration. Today, we are going to discuss about the impact of the voltage and frequency on the electromigration. So without any further delay, let's begin. Here we go with the menu for today. First, we will talk about the electromigration and voltage and introduction. Next, we will discuss about the impact of the voltage on electromigration in detail. And in the next section, we will talk about its mitigation. Next, very important concept, we will discuss what is a stress in VLSI circuits or any of the semiconductor circuits or any of the electronic circuits. Next, we will move on to the next section where we will discuss about the effect of frequency on electromigration and introduction. Next, we will go further deep by discussing the effect of unipolar pulsed DC waveform on electromigration. We will further analyze the effect of bipolar AC waveform on electromigration. Finally, we will move on to the conclusion. So folks, this is the menu for today. Without any further delay, let's begin. In this section, we will be talking about electromigration and voltage. Introduction. Increasingly small IC structures begin to have a significant negative impact on reliability because the cross-sectional areas of the metallic interconnects in the ICs are diminished in size. This is the scenario that is in present days we are going through right now. The problem arises because the required currents cannot be reduced to the same ratio and proportion even by reducing the supply voltage and gate capacitance. So if you are familiar with the ITRS technology roadmap where it is defined for each particular technology node, what will be the gate capacitance, what will be VDD, and all these minute details are there. So even in that particular roadmap, if we go and see, we will find that the currents cannot be bring down in the same ratio and proportion. In digital circuit, the voltage in the rails is constant for a particular technology node. So I just mentioned about the ITRS roadmap, right? If you go there, you will see that this VDD will remain constant for a particular technology node. For multi-VDD power domains inside a chip, the interaction points are balanced by level shifters. Nowadays, a lot of multi-VDD power domain chips are getting manufactured. So there we have generally a power management block which controls all the power going to different sections. They may have different VDD applicable to that particular block. So there we use level shifters. I just touch base this point because in today's scenario, this is also a very relevant information as compared to the previous bullet where I have mentioned for a particular technology node, the VDD must be remain constant. And in present scenario, how we deal with such different situation where we need a separate kind of VDD pair, we use a level shifter. In the digital plus analog mixed signal circuits, voltage level difference at the boundary are balanced by the A to D and D to A converters. Now in present days, the mixed signal chips here and there are a lot in production. If you look into them, what you will find that there are analog blocks which also coexist with the digital block. So the third point where we have said that VDD remains constant, that also get a bit changed because the analog circuit may require a different power supply voltage. And the voltage exchange in between these two blocks has to be exchanged with the interpreter, that is A to D or D to A converter, based on which direction the signal is propagating. So this is another important point. Signal nets are less wide than the power grid nets. I just re-emphasize this fact. For a power grid to function as intended, the voltage drop at each of its nodes should be smaller than a certain threshold. Otherwise, timing violation and logic failures may occur. Now, the voltage node means it is a circuit concept, not the physical chip concept. In a circuit, we have different nodes from where the branches go out into different directions, carrying the power to different parts of the circuit. Now, these nodes should remain static in terms of their voltage level. This threshold value as per the design rule manual. This all comes from the DRM, which comes from the foundry. We are done with this particular slide. Let's move on. Here we will discuss about the impact of voltage on electromigration. In last slide, we have talked about the basic fundamentals. Now, we will zoom in further down inside the circuit. In EM process, the voltage dependence of the resistance R as a function of V is expected to be a constant. It may have a positive slope due to the Joule heating. Usually, RV displays a positive slope corresponding to a negative curvature in the corresponding IV characteristic. Over the time, voids may be formed at locations with high tensile stress, which results in a resistance increase and voltage drop degradation. Let me explain this point. Due to electromigration, two things happen. One, a hillock is created or a void is created. Now, if a void is created, what will happen? The cross-section of the current carrying metal or via will get reduced and hence the resistance will increase. If the resistance get increased, the voltage drop degrades. So this is the way the things are happening. The power grid is deemed to have failed if the voltage drop at any grid node exceed a user specified threshold. We refer to this as a voltage failure. This all specifications come from the design as well as from the DRM. These things have to be maintained. The EM lifetime of the grid refers to the time at which the EM induced voltage failure is expected to happen. So this is the entire picture of the failure of a power grid in terms of the voltage. We are done with this particular slide, so let's move on. Let us continue the discussion with few more points. The critical volume of a void is the threshold above which the interconnect is permanently damaged. This is very much clear. The volume corresponds to a critical resistance rise that either two of the condition, let us see those two. First, causes a voltage drop across the interconnect to impair proper functioning of the circuit or leads to severe thermal damage generating out of Joule heating due to the power dissipation in the interconnect. In addition, the digital circuit are less sensitive to small voltage changes than their analog counterparts. This is we know very well. In digital, we have 0 and 1 level, and in analog, we have exact voltage. So the digital circuits are less impacted by the small voltage change. For the 0, generally we have a small band, and for 1, we also have a small band of voltage. So anything change within that particular band will not impact the particular level. The proper functioning of the digital logic depends essentially on the reliable differentiation between a few different digital logic states. Also, these circuits comprise a relatively small number of different types of subcircuits called gates. We have discussed a lot of points regarding the impact of the voltage on EM. It's a bit different than how the current is impacting on EM. You already know by all the points that have been discussed here. So let's move on to the next slide. Mitigation. When any problem comes to an engineer, the engineer finds a way to resolve it, and hence the term mitigation comes into the mind. In recent times, the wiring material was also changed from aluminium to copper due to its specific property. The lower specific resistance of copper resulted in a lower time constant, which gave rise to the higher signal frequencies. This in turn caused a lower voltage drop and lower self-heating in the interconnects. The changeover boosted overall electromigration robustness. We are done with this particular slide, so let's move on. We are done with the discussion of voltage impact on EM. Before going to the next section, here I will just touch base the concept of stress in an electronic circuit. When a circuit component, either active or passive, or interconnect, that is metal or via, is connected to either or combined under a constant voltage, under a constant current, under a constant temperature, we call it is under stress of that specific kind, whether it is pure or mixed. So this is the concept of stress. You will come across this particular term in the next section. That's why I explained this in a very simple manner. We are done with this particular slide, so let's move on to the next slide. In this section, we will be talking about the electromigration and frequency. Introduction. Damage caused by the electromigration, generally due to the unidirectional current. This is nothing but the DC current. So the basic physics on which the electromigration concept stands is derived by the DC current flow. Now, AC causes bidirectional current flow with change in the polarity. That's why it is called the alternating current. In two parts of a AC period, that is on time and off time, the direction of the flux of the electron wind is completely opposite. Those who don't know the concept of the electron wind, please watch the last episode. Here I have mentioned about this particular term, and also I have explained in the main episode. In VLSI designs, such periodic waveform, that is AC, comes from a clock and corresponding dependent signal transmission to the metal or via interconnects. An AC signal can be different nature, that is, of the varieties are unipolar pulsed DC, bipolar AC, and peak current. Each have their own way of response to the electromigration effect for metal or via. Here we are done with the particular slide. Let's move on to the next slide. Effect of the unipolar pulsed DC waveform. We can imagine the minimum void getting created due to the electron wind. This void creation time is less than the on-time period of the signal being transmitted. We add up faster of the growth of the void. Now folks, please remember we are talking about AC, so there will be a on period and there will be a off period because this is a unipolar pulsed DC waveform. On the other hand, if the time of the void creation is more than the on-time period of the signal being transmitted, then it will negatively affect the growth of the void. Negatively affects means that will reduce the growth, or the rate of growth will be less than the previous condition in the last bullet. When we are applying a very high frequency signal, the electron wind cannot react to the on and off periods and only feel an average current density. So by the last 2 points, you understand that a particular electron wind can contribute to a void if void creation time is less than on period. On the other hand, if the void creation time is much larger than the on time, then the rate of void creation will be reduced, and hence such waveform, if it has a high frequency, this means this change is very fast, then the electron wind going through the on and off period feels only the average current density. When the frequency is very low, automatic gradient is built up during the on-time period. During the off-time period, such atomic gradients brings relaxation. However, if the metal or via is much longer than the bleach length, this relaxation is insignificant compared to the EM-induced damage. So folks, we are done with this particular slide. So let's move on to the next slide. Effect of the bipolar AC waveform. If the frequency is less than a critical frequency, that is the frequency needs to react the DC equilibrium, the interconnect will follow DC-EM behavior. This is the condition for the bipolar AC waveform, where we have the AC swing both sides of the y=0 axis. And here comes term that is never heard before in the discussion of the electromigration. That is a critical frequency. When the frequency is beyond the critical frequency, that means the circuit operation frequency is much higher than the critical frequency, gradual enhancement in the mean time failure happens along with the frequency increment. Now, what do you mean by the enhancement in the mean time failure. That means the point of the failure go away from the origin, that is x equal to 0 or time equal to 0 point. In last episode, I have explained this mean time failure with the infographics. There I have explained this. So that point of the MTF will go away further. Such phenomenon results in improved effectiveness of the damage healing due to the reverse stress period. In a AC, right, when the swing is in opposite direction in the two part of the half cycles, the direction of the electron wind is completely opposite. So in one case, the electron will try to create a void, and in the another part of the swing, it will try to heal it. So this is the nature, because the direction of the electron wind is completely opposite, and hence the momentum transfer to the metal ions is also in a different direction. So if that momentum transfer is in different direction, then definitely in first half of the swing or in the positive swing, the void, whatever amount it was getting created, in the second half, that means the opposite swing, those voids be healed a bit. At the beginning of the positive and negative pulses, atoms and voids start to migrate along the grain boundaries or interfaces. This migration is able to recover with the opposite stress. Now here you can see the term stress, which I explained few slides back. And this stress means when a circuit is under operation, right, that particular circuit operates for a long time, and hence any of the stress could happen that I have explained in the last slide. A shorter stress period means a relatively smaller displacement of atoms and voids, which are easily healed. Material migration in one direction can partially migrate back to its original location under beneficial condition. Consequently, the interconnect suffers less damage from the electromigration under AC conditions. Here we are talking about the bipolar AC waveform. That means in the two half of the AC, one swing is completely in the opposite direction. Means that in the first half, if the swing is in the positive y-axis, in the second half, it will be in the negative y-axis. So in such condition, the last point applies. So folks, we are done with this particular slide. Let's move on. We continue here with few more points. Under ideal conditions, the magnitudes of both current and pain in the positive or negative half cycle, then no electromigration effect would takes place. So this is a very ideal condition. However, in real condition, there will be a little bit difference. Within a quite high frequency range, the damage healing process can overcome all defects which are brought during the other half of the period, and there should be no EM at all. Consequently, the MTF would go to infinity. So if you can recall the slide in the last episode where I have shown the infographics about the shifting of the MTF point, that point here in this particular bullet, as per the condition, will move towards the infinity. The lifetime of a metal or wire carrying alternating currents AC is significantly longer than the wire that with the direct currents DC due to the damage healing properties of the AC waveform that so far we have discussed. However, in high frequency AC current density has a DC offset. The DC component will determine the actual EM lifetime. In addition to this, the thermal stress due to the Joule heating alone will contribute to the degradation in the metal or via and lifetime based on the RMS current density. So even though you can see that the AC waveform has its own healing way of the void creation, however, its associations, the DC component or the Joule heating, both these things will contribute for the damage. The temperature gradients alone brings the metal ion flux divergence and cause the failure. So the void which we were getting earlier moving due to the electron wind, due to the momentum transfer to the ions, they will get the energy from the thermal conditions, and under the thermal stress, this void creation will get enhanced and damage will happen to the metal or via. In addition, the EM effect that is coming from the DC part of that particular AC will contribute to this damage. That's how the overall damage happens in an AC circuit. So folks, we are done with this particular slide. So let's move on to the next slide. Conclusion. At lower frequencies, on each half cycle, metal ions influenced by electron wind have ample time to migrate far out of the hot region into the cooler adjacent wear segments. Consequently, their thermal motion is largely frozen out upon reversal of the electron wind. Thus, damage is added up over the time elapsed. At higher frequencies, the switching time for the electron wind force direction is reduced. The hot junction can begin to experience reversible ion movement under reverse electron wind. However, high frequency AC current density has a DC offset. The DC component will determine the actual EM lifetime. Further damage is caused due to the accumulation of the Joule heating. We are done with this particular slide, so let's move on. If asked in interview, do you know the difference between static and dynamic IR-Drop analysis? Do you know the difference between SOC level IR-Drop analysis versus IP level IR-Drop analysis? Do you know what are the IR-Drop hotspots found inside a chip? Let's start our journey to know all the answers. Hey guys, welcome back. In today's episode, we are going to discuss below points. Power delivery network, significance on IR-Drop analysis. Next, we will cover the definitions of IR-Drop and ground bounds. Next, we will show the position of IR-Drop in both the design flows of the IP design as well as ASIC design flow. Next, we will touch base on some of the fundamentals of resistance, ACL, AVL, and circuit and parasitics. Next, we'll do a classification of static and dynamic IR-Drop analysis. Next, we will show the IR-Drop and its impact on the timing analysis. Next, we will talk about the IR-Drop effects to be found for multiple power domains. Finally, we will talk about the IR-Drop thermal hotspot detections and its mitigation methods. So, that's the menu for today. Without any further delay, let's begin. Introduction. For continuous downsizing of the technology nodes, the chip operating frequency is continuously increasing, at which the timing-related defects coming out of high-speed tests are high in proportion. Now, folks, you might have noticed that today your mobile phone processor, the gigahertz processing speed is increasing with every new generation, and IR-Drops are very much relevant for this high-speed switching operation. We'll come to that point later. DFT techniques may cause the test vectors to contain non-functional states, which result in higher switching activities compared to the functional modes of operation. Specific scenario. Excessive switching activity causes higher power dissipation, which in turn may cause IR-Drop hotspots that could damage the circuit. Due to the higher IR-Drops, which increase signal propagation delays during the test, causing field loss. Power delivery network. The power grid simulation in ASIC causes power delivery network, abbreviated as PDN, to turn on all the leaf cells inside any VLSI circuit. Here is a short and sweet diagram of the power delivery network, which is easy to understand. Now, let me point out the parts and components of this power delivery network. This is power ring. There are two types of power rings, since we have shown in two different colors. One is VDD, another one is VSS. Next is the power strip. Here, these take out lines from the power rings into the cells. So, there are again two colors because of the two different supply voltage, that is VDD and VSS. This one is called IO pad. This one is called IO pillar. This one is called corner cell. And this area is the core where our silicon chip resides. So, the power delivery network, as you can see from the figure, distributes the power, that is VDD and VSS lines, into the core area. IR-Drop is excess voltage drop caused by parasitic RLC of the metal routes from the PDN, happening even before the desired voltage can reach the target power pins of the standard cell, IP blocks or macro blocks. So, as per this particular definition, the IR-Drop happens well before the actual voltage from the power rings, as shown in the right hand side, could reach up to the specific standard cell or macro blocks of any IP block to the power strip. Power buses carry large DC current, causing the large IR drop, which in turn gradually reduces VDD towards the center of a chip when the power supply is driven by pads around the perimeter. So here in this slide, we have shown you the short and sweet diagram of a power delivery network and explained in a nutshell how IR drop happens through this power delivery network. IR drop and ground bounce. The total IR drop is further divided into resistive and inductive subcomponents. Here is a simple graph to explain the two subdivisions. This is our VDD line. This is our ground line. Now, the resistive voltage drop, also known as on-chip IR drop, is mostly due to the voltage drop because of the on-chip metal or via interconnect resistance. Here in this diagram, this small drop is called the IR drop. The inductive drop, also known as the DIDT noise, is mostly caused by the in-package inductor. The DIDT noise, often referred to as simultaneous switching noise, also known as ground bounce, which is caused by rapid changes in the current passing through the parasitic inductors in the power network. And here in this figure, this bump is the ground bounce. So you can see the two components of the IR drop, the total IR drop, are shown in the right hand side figure with a drop and a bump, or the VDD line and the ground line. Both of these contributes to the IR drop as a whole. So we are done with this particular slide. Let's move on to the next slide. IR drop in IP or analog design and ASIC design. Here in this slide, our flow proceeds in the direction of this arrow, and in the left hand side we will keep the IP design or the analog design flow, and in the right hand side we will keep the ASIC design flow. Here the graphics are used as a symbolical meaning so that you can identify easily whatever I have just mentioned now. So first, in the IP or the analog design part, the schematic design is done by the designers. Next, we draw the layout by hand. Next, we do the ERC and LVS check on the layout and make sure that the layout is clean of any DRC or LVS violations. Next, we do the parasitic extraction, abbreviated as EX, and other set of physical verification. Next, we do the EM and IR drop analysis. Generally, these two are paid or analyzed side by side because of their similarity in their nature. In this channel, I have already created one episode on EM analysis in both the IP or ASIC design flow. Next, in this flow comes characterization and delivery. So, because this is an IP, you have to characterize it, means the electrical characterization and final packaging of this IP. So, we are done with the flow of the IP design. Let us move on to the ASIC design flow. First, there is a front-end design part. We are not going in a detail because that would take much more space and not very much relevant in this particular case. Next, we do the floor planning and PNR. As we proceed further in the back-end side, we have the ERC and LVS check after the floor planning, PNR, and the layout is done. This step makes sure that the layout is ERC and LVS clean. Next, we have the parasitic extraction, abbreviated as PEX, and rest of the physical verification checks. In the next step, we do the EM and IR drop analysis. Finally, we do the formal verification and we proceed towards the sign-off. So, you can see that the IR drop analysis is performed in both IP level as well as the ASIC design level in this particular highlighted step. The purpose of this particular slide is done. So let's move on to the next slide. Resistance of metal strip and ACL AVL. Here in this slide, we'll look back and touch base some of our fundamental concepts which will help you to understand the IR drop analysis and phenomena altogether. We have a very close relation of the current, resistance and voltage. That is I, R and V. You can see the triangle, and we can have several combinations with these three particular components in multiple expressions of a circuit. Next, this is a metal wire, and this is very much similar to the metal routes where the resistivity rho is A into R by L. Is the cross-sectional area, A is the length, R is the resistance. This is a very fundamental concept, and this concept is used as is in the resistance calculation of the metal routes in the BEOL part of the chip design process. So the next one is ACL, that is Kirchhoff's current law. where we know that the sum of all the currents reaching to a particular node is 0, which we can express by a equation that is I1 plus I2 is equal to I3. As per the direction, whatever currents coming towards the node here shown in the picture is leaving the node. All these concepts are very much important in the IR-Drop analysis, and we are going to give further in further slides. The KVL, that is Kirchhoff's voltage law, also we can imagine from this circuit here. You can see some of the all voltage drops equal, that is I in inverse as well as the recipe. So I have touched base the basic physics here in this particular slide so that you can now correlate in a very fine gradient concept of IR-Drop analysis in upcoming slides. So we are done with this particular slide. Let's move on. Simple circuit diagram and parasitic. This is our simple circuit diagram where we are using the MOS, and this is without parasitics. This is just for your understanding here. And once we have the post layout version, that means layout is done, we are done with the DRC LVS and we have extracted in the parasitic extraction process, that is PEX. We have with parasitics, that means circuit plus extracted parasitics because of the actual layout or the wiring that come in a real picture of a chip. Simple circuit shown in the left hand side becomes like this, where you have a lot of resistance and capacitances here. You can see in the right hand side it's very clearly shown here, although this is not explicit. However, this is a very exemplary purpose. This is how the resistances and capacitances will come around any node that we are working. Also, again, I emphasize this is not an actual case or actual circuit. This is just for your understanding how the parasitics in the post layout process will come and get attached to different nodes, because these parasitics will contribute for the EM and IR. We're done with this particular slide. Let's move on to the next slide. IR-Drop classification. So we have our IR-Drop grossly aggregated in two parts. First one is the static one, that is static IR-Drop, and the next one is the dynamic IR-Drop. So this very simple classification. Now in upcoming slide, we will touch base both a static and dynamic IR-Drop analysis one by one. We are done with this particular slide. Let's move on to the static IR-Drop analysis. The IR-Drop is defined as the I average into the resistance segment, that is R-ware segment. Here I mentioned the word static. Here IR-Drop static means the static IR-Drop, and I average well-known quantities, average current you have come across already in your textbook. And resistance R-ware segment, we have just shown you in the pictorial representation what the resistance segment looks like for a metal drop. Now this I average is all factors out of the leakage currents. Here you can see a simple representation of various metal layers that is going through. So if we say the horizontal ones, the first one here it will be 1, metal 2, B, and this could be metal 4. However, you can see inside I have drawn the resistances. Once the parasitic extraction tool prints up any of the metal out, it will split into multiple resistors, and they will be connected in the either in the TSPF or in the F file as like this. So resistance 1, resistance 2, resistance. If you see their nodes, they will be also in the synchronous of connectivity. So this is a simple picture of the R-ware segment that you can imagine, and the power delivery network part. When the power comes in, I have shown few slides back as a pictorial. With that and this in the mind, and then proceed for our next explanation points. Static IR-Drop is an average voltage drop for the design, hence it is stimulus vector dependent. Vectors are taken from 1, the switching probabilities of each cell, and number 2, applied switching probability of initial cell. The average current depends totally on the time period of the clock. This is very fundamental. If you go back in the definition of I average current, you will find out in the mathematical expression. Static IR-Drop is dependent on the RC of the power grid connecting the power supply to the respective standard cell. That is what I mentioned, that we already have shown up PDN few slides back, and this metal route, you can see that all these things will be coupled together for IR-Drop analysis. We're done with the particular slide. On to the next slide for few further points on static IR-Drop. The PDN reduced to a resistive network, and a voltage drop across this resistive network is calculated based on a given current source. Loads are assumed to be driven by PDN. The static IR-Drop is performed around all the production RC and PVT corners combined. So I have two separate episodes about the RC corners and the PVT corners in the same VLSI FAQ. You can find out them in the FAQ playlist. In case you are not familiar with the RC and PVT corners, please go ahead and watch to have an in-depth knowledge. In VLSI, the static IR-Drop is performed across all the combination from RC and PVT corners, so that we have the full coverage. Next, gate channel leakage current is the major reason for the static IR drop. Another good point. Static IR drop was good or sign of analysis in older technology node, where the sufficient natural decoupling capacitance from the power network and non-switching logic was available. About the nodes which are beyond 130 nanometer, higher than 130 nanometer, or 9, all those technology on below. Right now, today we are on below 10 nanometer. Dynamic IR drop is a lot of signal. That's why we have the point. Sometimes switching factors can derive from the functional waveforms of the SAFE or the VCD files. We are done with this particular static IR drop analysis. Now let's move on to the dynamic IR drop analysis. Dynamic IR drop. Unlike static method, in reality, no two cells inside chip receive the same supply voltage due to placement, nearby cell activity, and dynamic nature of its operation. So here you can see one simple diagram. Here is our clock pulse. The black line horizontal is our ideal VDD, and the red line with the wings is our real VDD, which is in sync with the clock pulse. You can see here. Here in x-axis we have kept the time, and in y-axis we have kept the voltage. Although you cannot see the x and y-axis here. Now I have shown you the VDD, and the black line horizontal is our ideal ground. And the line with the wings that is shown in green, that's why I have kept the color same, is our real ground. So these are the two things you are going to get explanations in the upcoming points. Thus, each standard cell have its unique dynamic voltage signature for the power or the ground pin. Cycle to cycle, the dynamic voltage variation depends on overall change in the peak current, which causes the RLC oscillation or noise in the board or IC packaging. You can understand the swings that shown in the right hand side picture, that is in the real VDD and real ground, comes from the RLC oscillation or noise. Number 2, change in the toggle rate of the local cells, which could result in temporary depletion of charge and high frequency noise drop. We have covered some points. We are yet to cover further more points on dynamic IR drop. So let's move on to the next slide. Here, the PDN is modeled as a network of the impedance and time domain or transient analysis is done. And see in the right hand side, I have said that we have kept the time in the x-axis. And when we do any analysis with respect to time, it referred as the transient analysis. So because of the RLC and we are seeing the swings, we do the transient analysis on the PDN. And the PDN is seen as the combination of the RLC. Those are parasitics. Those are not from the design intended point of view. Here, the IR drop is caused by high-speed switching transistor inside logic cells. Peak current demand puts off when a large number of circuitry switches at the same time. Hence, dynamic IR drop is less dependent on a clock period and can't be modeled by pure traditional static timing analysis. So you can see from the right hand side, there will be a lot of swings that is coming out of the RLC, and this would cause a peak current shoot off, and that's very much related with the dynamic IR drop analysis. And this is dynamic in nature, that is time, so it cannot be modeled with the static timing analysis, where we are performing everything in static manner. That means all are pre-characterized values and not in the on-the-go analysis that we do in our transient analysis. So in case you have some confusions about the static timing analysis, we also have a playlist in this channel. So go there into the playlist and start from first episode. There are a couple of episodes which contains the theoretical part, and as well as we cover the hands-on practical lectures here in the playlist. So go ahead and watch them. Preventive IR drop analysis and investigative analysis is phase pattern specific. Here, whatever the dynamic thing we are dealing with is very much dependent on the test pattern. Why we talk about test pattern? Because the high switching frequency that we are talking about in the context of dynamic IR drop comes from various test patterns that we can generate. Those detections of the dynamic IR drop will be through the test patterns of various kinds. So done with this particular slide. Let's move on to the next slide. IR drop and timing analysis. Undetected IR drop can be compensated by means of increasing the supply. Extreme cases, this would lead also to timing analysis failure, whose root cause is a higher voltage drop above specified threshold or margin. Dynamic IR drop neither can be detected nor can be modeled by static timing analysis. Altogether, the IR drop can cause setup violations on the data path signals. Here is our example from the STA playlist, where we have shown the setup violation using the OpenTimer tool. And IR drop can cause hold time violations on the clock tree network. Here in the playlist, we have also shown the code violation using the OpenTimer tool, and these are the explanation or snapshots from the episodes in the STA playlist. Delay of a cell depends on the voltage difference, that is VDD minus VSS, both functions of T. That means both are transient, as we have shown in the slide before. This delay increases with the increase of standard cell threshold voltage, while we vary the threshold voltage in a manner for the standard cell for the different categories like ULVT, LVT, SVT, HVT and UHVT. These are various standard cell packages for different threshold voltage. ULVT is the ultra low VT, LVT is low VT, SVT is the standard threshold voltage, HVT is the high threshold voltage, and UHVT is ultra high threshold voltage. So keeping all the points in mind, and see that with the hit on the setup and hold violation as well as in the delay, altogether the timing analysis is get affected by the IR-Drop happening in an actual chip. We are done with this particular slide. Let's move on to the next. IR-Drop with multiple power domains. Power distribution among multiple power domain, P is the abbreviation, in a single chip is significant in floor planning and placement phases. So here you can see one diagram, that is a block diagram for a power domain blocks in a chip. So let me bring out my mouse. So whenever we have different power domains, we have a controlling block called the power management block, and here PD1, that is the power domain 1, will have VDD1, PD2 will have the VDD2, PD3 will have the VDD3. So I have just named it maybe a digital block, analog block, and some macro that you have purchased from your another vendor. This is a typical representation of the different power domains. I have explained about the power domains in detail in the UPF series, and you can find the lectures on the UPF in the UPF playlist of this channel. Proceeding forward, the next point is the PNR tool synthesizes the power distribution network based on the power budget specification for each domain while keeping the power network constraint under consideration. Because of all the blocks you can see in the right hand side picture, budgeting has to be in a proper way so that proper voltage, if there are 3 different VDDs in a single circuit, they will receive in a proper manner. IR-Drop map is used to analyze the power network. We'll later come to the IR-Drop map. If analyzed maximum IR-Drop is not acceptable, then reconstraint and resynthesize are done. So these are engineering changes that we do as per our analysis the IR-Drop. After the IR-Drop becomes acceptable, the new floor plan is created with added power or ground pad. I have shown the pads in the first or second slide in this particular lecture. So we are done with the cases of multiple power domains and how the budgeting and all the things we deal with the different power domains when we have in a how we approach the situations. It's just discussed here in this slide. We are done here. Let's move on to the next slide. Thermal hotspot by IR-Drop. The heat produced in a chip is proportional to the dissipated power. That is what I touched base in the fundamental slide where I have shown the relation of V, I and R. So I square R is power dissipation which causes the heat, and all those things we have done in our fundamentals in our textbook. An excessive power dissipation during the operation will increase the circuit temperature well beyond the safe zone, causing the permanent physical damage. Such zones are predicted by dynamic IR-Drop analysis and referred to as hotspots. Now, how do they look? They look like this. So you can see different colors. And these are heat signatures predicted by IR-Drop analysis inside a chip. So you can see there are different color gradients here in the right hand side picture. Generally from green towards the red, we more approach the more hot regions are there. So this thermal signature is kind of similar to if you see the infrared detection of heat sometimes used in medical sciences. The videos where a human body temperature is scanned by the different scanners. So there you also find some similar heat signatures. They are then kind of color gradients are used. Here we do it by the IR-Drop analysis tool, and we have a similar kind of heat signature happening inside the entire chip. We have some zones which are less heated. We have some zones which are extremely heated here in the highest color, the red. So obviously the tool will give you the legends about the power ratings and dissipations happening for each of the color. So this is the heat signature. These are called the thermal hotspots, where different spots inside the chip can get heated, and over time they are not cured, then they will cause the permanent damage. That is the purpose of the IR-Drop analysis, to detect these hotspots and correct them way before the sign off. Thermal gradients are hotspot due to the various different functional blocks with different power dissipation over current or voltage stress for a long time of continuous. Generally, our chips, if it is a handheld device, they are switched off. But in case of, say, network routers or servers, they will be kept on and on for a long time. So these are under the constant current or voltage stress. So if any hotspot generates in such a chip, over time, they will grow and become fat. And the damage will happen to a larger part of the circuitry. All these thermal hotspots are detected by dynamic IR-Drop analysis, and they are cured by the engineering changes so that things are well taken care before the chip goes into the hands of the end customer. Here we are done with this particular slide. Let's move on to the next slide. Here in this slide, we'll talk about the IR-Drop mitigation. So far, we have discussed about all the reasons behind IR-Drop, how we detect the IR-Drop, and our detection procedure theories we have covered so far. Now, here in this slide, we'll talk about some of the mitigation methods in the upcoming points. High IR-Drop impact on the clock tree network, causing the hold time violation, while the IR-Drop data path signal nets are caused data time violation. I've also touched this particular point, few slides back. To deal with such situation, one may separate the standard cells with high switching activity apart so that the burden on a given bump feed many standard cells can be mitigated. The lines coming from IO pad into the power rings and then going for strips, those will be well taken care if separate out zones where there is a higher switching activity and there is a less switching activity. So chances will be less of getting hotspots and the circuit will be cured of the IR-Drop violation. And these are the methods, the engineering changes we are going through in this IR-Drop mitigation slide. With padding, clock cells technique, clock buffers or inverters and clock gate cells are given extra space to keep out regions to avoid placement of standard cells and any excessive cell density around them. Decap, that is decoupling capacitor, insertion around the cells within a dynamic IR-Drop hotspot region is another way of mitigation. High driving strength standard cell create a dynamic IR-Drop issue because if the driving strength is high, it will draw more current and cause a more dynamic IR-Drop in the long run with respect to the time. Field padding is used for these cells, or we insert the decap cells around them to mitigate the IR-Drop. So these are few examples of the engineering changes after we detect the IR-Drop hotspots through a preventive analysis. In case we find the hotspots, we apply one of these techniques. Sometimes as per the design and case by case basis, here you can find a different solution as per your own work experience. So please let me know in the comment you have used some other techniques for IR-Drop mitigations to share with others. We're done with this particular slide. Let's move on to the next slide. Summary. Here let me summarize the entire discussion we have done so far in the past slides in this episode. Most of the times, the undetected silicon IR-Drop may lead to appropriate voltage not reaching the transistor in CMOS. Very simple point, because if the drop happens, that amount of voltage is subtracted from the power line and the end cell, the leaf cell will not get the desired amount of voltage because of the KVL, right? This can be compensated by increasing the supply voltage but may contribute to the timing analysis failure for extreme cases. If the IR-Drop exceeds a specified threshold, typically say 10% of the VDD, the chip could become defective, the kind of de facto standards that we use in a design house. IR-Drop analysis is necessary for both at the block level and the chip level to assimilate preventive design strategy. IR-Drop gets to be bigger problem as lower supply voltages are used in lower technology node. IR-Drops in metal routes cause the wires to heat up. Oxide is a good heat insulator, so over time, IR-Drop may build up heat in the metal routes. This can degrade metal wires resistance and performance over time. When the wires get hotter, they become more resistive, causing more IR-Drops and more heat until the wire melts down. For thermal runaway, this may cause burnout problem. So we are done with this particular slide. Let's move on.
If asked in interview, do you know what is ground bounce? Do you know what are the factors in a chip that controls the ground bounce? Do you know the methods which can mitigate the ground bounce? Let's start our journey to know all the answers.
Hey guys, welcome back. In today's episode, we are going to discuss the below points. First, we will do an introduction to the concept of the ground bounce. Next, we will do the correlation of power and ground bounce. Next, we will walk through couple of techniques through which we can mitigate the ground bounce. Next, we will highlight the power gating technique, which is one of the most used mitigation techniques for ground bounce. And our episode will end at this point. Here we are done with our menu for today. Without any further delay, let's begin. Introduction. Power supply noise and ground bounce can cause considerable path delay variation in VLSI circuit. Generally, we have two lines, that is VDD and ground, right, in any VLSI circuit. So noise in either can cause path delay, that is delay in the timing in any of the VLSI circuit. And if there is a delay, then it affects the performance of the chip. So here is the grave importance of dealing with the ground bounce. Ground bouncing noise is the primary cause of false switching in high-speed circuit and a major cause of poor signal quality. This is the immediate impact. This one is the ultimate impact, and this is the immediate impact of the ground bounce. Through the shared ground or power distributed network during the wake-up event, the bouncing noise generated in one of the power domain is transferred to the active block, which will flip the logic states. So in some episodes, I have discussed about the power domain. I'll provide the link in the description. Please watch it for understanding the power domain. Now, when one particular power domain is in the sleep state, that means we have several blocks, right? When a particular block is there and it is waking up because of the external signal, or maybe some sequence of the signals that is already there is coming from a particular block. So during that particular event, these things can go, this false switching and noise, all these things from one block to the another. And it can flip the logic gate state. That means it can flip 1 to 0 or 0 to 1. That means it actually disturbs data transmission inside among the different blocks. And definitely that will be a functional failure. This noise is known as ground bounce noise. Whatever we have talked about, right? All these effects are summed up as ground bounce noise. Generally, any disease is detected by the symptoms. So we have talked about the symptoms, and the disease is a ground bounce. Major component of the circuit noise is inductive noise. Now we are entering into the classification. What type of noise they or impact they within the circuit and impact the circuit. Here is an inductive noise. It is a critical and challenging design task to control the amount of the inductive noise that is transferred into the power planes. Here we are done with this particular slide. Let's move on to the next slide. In the next slide, we are still continuing the introduction. Package pins, bounding wires, and on-chip IC interconnects all have parasitic induct. We were talking about one of the root cause, which is the inductance noise, right? So where does it come from? It comes from the parasitic induct. Like we have parasitic R and C extracted during the PAF extraction or DSPF extraction. Similarly, yes, we can also extract the inductance. That inductance does stay within the VLSI chip, and this causes ground bounce. When an inductor current experiences time domain variation, a voltage fluctuation is generated across the inductor. Now, what is a time domain variation? That means we have a transient behavior. Any circuit behavior that is changing with time that impacts inductor. Because if you remember your class book, right, there is a transient response for the both RC circuit and the RLC circuit. When the RC and L coexist in the VLSI chip, obviously the transient effect will impact all of them, and in return they will generate some bad effects, one of which is the ground bounce. This voltage is proportional to the inductance of the chip package interface and the rate of change of the current. We are very specific here, nothing more to say for this point. As a result, when the logic cells in a circuit are switched on and off, the voltage levels at the power distribution lines of the circuit, it is also very, very plain and simple. If we have a noise, it is going constant, right? If we have a noise going like that, obviously this level will be impacted by the superimpose of the noise that is stating here. This inductive noise, sometimes referred to as the simultaneous switching noise, because it is most pronounced when the large number of I/O drivers switch simultaneous. Now we are talking about the chip packaging where the I/Os are there and the inductance comes from that particular point, and we coin a term called simultaneous switching. And it is nothing but the inductive noise, right? The I/O pads or connection of the wires, they are there, they exist there. And that wires interconnects, they also contribute to. So, apart from the parasitic inductors coming from the silicon. We also have the IO pads and somewhere the inductance behind the ground bounds does exist. Now here we have talked about the general concept of the ground bounds through the introduction, and we have given some of the background reasonings why the ground bounds happen. So let's move on to the next slide. We are done here. Correlation of the power and ground bounds. As the noise comes in, the noise affects both the power rails, that means the VDD as well as the ground. So how does it looks? It looks like this, and I'm explaining here. So this is our VDD line, this is our GND line, and the noise is occurring there. We generally refer to it as the voltage drop, and if it is impacting the ground line, GND line, then this noise will be termed as ground bounce. The ground bounce is nothing but ground noise. Power bounce is the noise glitch on the power line, is the power bounce. When ground bounce and the power bounce are in phase is the common mode noise, they will not affect the local logical cells, but will degrade the signaling between the distance transmitter and receiver, that is TX and RX. Generally, if these two are in phase, this one and one is in phase, it will not impact the immediate circuit. Rather, if we have a block here, which is the TX, right? TX, and we have a block at other point of circuit, RA, and right, the VLSI wirings inside a chip runs in the length of kilometers, although the chip had all the routing. So when a trans signal is going on, if we interpret the signal here and here, these two signals here and here may show a difference because of the ground bounce, the power bounce noise. So that in turn impact the signal exchange between the TX and R. When ground bounce and the power bounce are out of phase, differential mode noise, out of phase, they adversely affect the local logical cells, causing jitter in timing circuit. When these two, right, these two are out of phase, not in the same phase, they will be impacting the local logical cells. That means which are there maybe in the path, or maybe there is some, here is our TX, right, and here. This path, it may not be aware at all, and there might be circuitry which is processing the signal before going to the RX, and also it can impact the logic cells here, right? Because we don't know how our chip is there, how it is designed. We are giving a general guideline here. You are the best judge when you are working on your chip. You can actually interpret these concepts into your theory. Ground bounce mitigation techniques. Many design techniques have been used to reduce the effect of the ground bounce, such as power gating technique, stacking power gating technique, various empty CMOS technique. These are nothing but multi-threshold CMOS, adding decoupling capacitors, that is decap, having separate ground buses for IO buffers and internal circuitry, widening ground interconnect buses, evenly distributing circuitry among power and ground. Previously, in couple of slides, we have talked about the ground bounce and the visual representation of it and the in-depth impact of it. And here we have listed couple of methods which are used in the VLSI design area for different kinds of needs and different kinds of circuitry to combat the, as this is a short episode about the ground bounce, we are not able to accommodate all of these techniques and their details. In case you need them, just please write down in the comments. We will create more FAQ episodes per topic basis. That means if you are asking, we will create for each of them here in this page. However, we will touch base one of the most used technique, that is power gating technique. We're done here. Let's move on to the next slide. Power gating technique. We are touch basing here in this particular slide about the power gating technique, which is one of the very popular method to tackle with the ground bounce. Power gating technique is widely used in VLSI to significantly block the leakage currents in standby or sleep mode. Here, a sleep transistor is added between the actual ground rail and actual circuit ground, also known as the virtual ground. Since we are giving a brief description, we are not diving deep. We are just touch basing, so have to survive with all these short and sweet descriptions. And to understand from these 2 points, right? This method is for the sleep mode, right? And how it is done? First, we add a sleep transistor between the actual ground rail and the actual circuit ground, also known as virtual ground. During the sleep mode, this device is turned off, cut off the leakage path from the ground. So it cuts off the ground path. Hence, no noise is coming from ground, and hence the power and the ground bounce, but mostly the ground bounce is blocked, right? Here, power supply causes virtual ground rail to charge up close to supply voltage VDD, which in turn suppresses the leakage. This is another part of this. However, when the sleep transistor is turned on, the virtual ground rail is restored to its act. This way, the restoration happens, that we open up the channel again. This way, we control the entrance of the ground bounce noise into a particular block or into couple of blocks. Here we are done with this particular slide, giving you a brief description of the power getting technique. Let's move on to the next slide. Hey guys. Welcome back. In today's episode, we are going to discuss the below points. First, we'll talk about what is ESD. We will go in detail with 2 slides. We have much more detail on ESD. Next, we'll talk about the ESD damage and protection, the general topic, and also we will cover various types of damages that can happen to your chip. Next, we will talk about the qualities of a good ESD protector. Whatever ESD protection we are using, what should be the good criterions for that. Next, we will talk about the ESD protection, whatever done in the VLSI design. That means the VLSI design stage where we incorporate the ESD protection. Next, we'll talk about the various ESD protection methodology as per the circuit theory, diodes, stack diodes, etc. Next, we will go in detail for the ESD protection scheme of snapback devices. One of the most popular snapback devices which is used is SCR. Next, we will talk about another snapback device, that is GG-NMOS, that is gate grounded NMOS. Finally, we will cover the various ESD protection scheme, that is the type of different clamps that are used for the ESD protection. In today's episode, first we will talk about the ESD damages and qualities of the good ESD protection, and in the next section we will talk about what we do in the VLSI design, and we will go up to the cell level where we use the different devices to protect the ESD, and we will talk about various schemes that are used to protect the ESD. So here we are done with the menu. Let's move forward to the next slide. What is ESD? The most famous type of ESD, that is the large scale lightning, which volts up to 10 to the power 7 volt and currents up to 30 kiloampere. So this phenomena happens in front of your eyes in the rainy season when the lightning strikes. So that is the good example of visible ESD. However, when we are talking about ESD in IC, that is the VLSI, we are talking about the ESD that you cannot visualize, that happens only inside the circuit and at the very miniature level. However, in your day-to-day life, the largest and the biggest ESD, that is the electrostatic discharge, that you can see is the lightning, which has a voltage in order of 10 to the power 7 volt and ampere in order of 30 kiloampere. Now, electrostatic charging of two objects result from electron transfer during the friction. So this is the basic physics that happens for a electrostatic charging phenomena. And once any two objects are under the friction, they are oppositely charged, and that charge could get discharged through the electrostatic discharge process. Here is our circuit, and you can see here we have various components, like we have transistor, IC, etc. And whenever your body is charged and you touch the device, suddenly that electrostatic zap, that is the discharge, will enter into the entire circuit board, and it may damage your transistor, it may damage the IC or any other component which is susceptible to the electrostatic discharge. ESD is an electrostatic event which balances the charge potential difference between the two charged objects of opposite polarity, leads to high current in a very short time. This high current in a very short time we will talk about in next couple of slides, where we will show you the graph. In this slide we saw the phenomena that actually physically that is occurring here when you are touching any circuit with your hand, bare hand, and that actually does the ESD. So those electronic engineers who actually do this kind of assembling and handling these circuits, they use a electrostatic strap that they tie to their hand and which is connected to the ground, and with maybe in both hands they have two different ESD straps, so that the human body is electrostatically protected, so that your touching any device will not damage. So such kind of electrostatic straps are used in the electronic industry where electronic circuits are packaged and assembled. This is just for your knowledge. On an average, ESD destroys about 20% of electronic components before they are installed into a system. So this is what I was talking about, that wearing an electrostatic trap in the electronic industry helps the circuit to get prevented from the damage. After assembly, anywhere from 33 to 70% digital devices fail soon after consumer purchase because ESD may only damage a component, but it opens the door for the further subsequent damages within brief time during the circuit operation. So ESD has two levels of damages. First thing, it damages the circuit. Whenever you are touching this circuit, it may damage this transistor and it may partially damage this IC, maybe this pin or the circuitry which is tied to this pin. As soon as we connect the power to this board and entire circuit is in operation, this IC will fail within maybe few seconds of operation. That means this one get fully damaged due to the ESD and this get partially, and whichever component is partially damaged can become fully damaged during the circuit operation. So this is the risk of the ESD, and hence in electronic industry people wear electrostatic straps onto their hands so that the circuit which is getting assembled should not catch any ESD damage. We are done with this particular slide. Let's move on to the next slide. Here we are still continuing on the topic what is ESD, and let us go to the next point. A person can acquire charge by simply walking inside a room. Now this is very dangerous. Even you are walking inside a room with the objects that around you, you can get charged electrostatically. When such charged person or object approaches a grounded conductor, for example a pin of a packaged integrated circuit, that is IC, an electrostatic discharge event can occur. This is characterized by high current in order of ampere within few nanoseconds. And here is the graph that I just spoke in last slide. So here, this is the transient response of the ESD, because here in this x-axis we have time and in y-axis we have current. Although absolute values I have not marked here, just for your understanding, you can see initially there will be a first peak where the entire set of charge getting discharged, and there can be a secondary peak. The secondary peak can also be there. So the circuit may first get a high peak, a sharp peak that injects the charges into the circuit, which can damage multiple objects, and there is a secondary peak again which can damage a secondary level damage to maybe the same component or maybe some other component. So this is the typical transient characteristics of the ESD current. A high current density and or electric field, so sorry, here there is a spelling mistake, can damage the conductor, semiconductor and insulator of an IC. So whatever components are there, anything, whether it is a conductor, semiconductor, insulator, they can get damaged to the ESD event that happens within a fraction of a second. A human sensory perception cannot recognize the several thousand volt that is getting discharged through the ESD. So we are not capable of sensing the ESD. That is our incapability. And that's why if you are working in an electronic assembling industry where you are assembling different circuit boards or soldering different circuit boards or any kind of activities that is related to onto the PCB or actual packaging of the circuit, that time you are advisable to wear an electrostatic strap onto your two hands separately, so that any of your hand is not electrostatically charged and the circuit on which you are working, that should not get damaged. The circuit present inside the IC will tend to be partially damaged or might break down when this high voltage pulse enters. This can happen to the IC whichever we are dealing with inside, which is maybe inside in the PCB or maybe inside the phone that is you are handling. Now there is another thing that you can notice day-to-day things, that whenever you are purchasing a RAM, you are purchasing a hard disk, you get in a bag which is maybe of in a graphite color. So those bags are electrostatic bags. Means those bags are electrostatic proof bags inside which the hard disk or the RAM, all these semiconductor things or maybe the computer equipments, all they are packaged in the electrostatic safe bags. So those are also used in the industry for protection. Those are external protection. However, in today's discussion we will talk about the internal protection. That means a circuit should be internally protected from the external ESD injection. So here we are done with this particular slide. Let's move on to the next slide. ESD damage and protection. So let us talk about ESD damage and protection. ESD in an IC usually start with oxide breakdown through percussion path. So generally there is a MOS structure, right? Metal, oxide and semiconductor structure. So this oxide, right? The ESD enters, right? It will create a zigzag path inside it through which the charge will cross, and this is damaged, and the name of this path is called the percussion path. The high current density damages the semiconductor devices through thin film fusing and filamentation and junction spiking. So all these things happen when the ESD event happens in a semiconductor chip or device, whatever you call. The high electric field, on the other hand, can cause the failure through dielectric breakdown or charge injection. So dielectric means oxide here, and there could be some other dielectric which also can get damaged. Not only the MOS structure, but several other oxides are there to protect the different parts of the IC. Also, those can get damaged. Hence, necessary components are used to protect ESD so that the destruction of a product or a system when touched can be eliminated. That means the inside protection to a circuit is given for the ESD event. However, external protection like ESD straps or ESD protection bags that I have just talked about are provided. Internally, we also provide the mechanism to fight the ESD. Due to this factor, there is a strict packaging, handling and design requirements of suppliers by government and other companies. I have talked about again and again about the different safety measures, which I have just repeated with a point here. Here you can see the typical protection method for the ESD. So here we have diodes here we will talk about later, and you can see there is a clamp, and here is our core of the circuit. Here is our IO pad, VDD pad, and this is our VSS pad, and these are the power rails. These two are power rails. So this way we provide the different mechanism we will explain in later slides. This image is just for your reference, and let's move on to the next point. The right hand side picture shows the typical IO schematics protected by the ESD cells. These are the pads which are actually connected in the IC periphery. And here is our core of the circuit and clamp. So this is kind of typical arrangement that we have in our ESD protection schemes. We are done here. Let's move on to the next slide. Various ESD damages. Junction burnout is caused by the injection of the ESD transient of sufficient energy and duration to force the junction into secondary breakdown. So junction means it could be a PN junction or some other type of junction which can get burned out. Junction burnout is often characterized by high reverse bias leakage current or a total short. It can be characterized by a reverse bias operation of a junction, or it could be simply become a short. Oxide punch through is the major category of the ESD damage. Now, when you are testing any PN diode with a multimeter, if both sides giving the continuity beep, that means that PN junction diode, the junction, that means the P and N junction is short there. Whether it is damaged by ESD or something like that, this is a physical phenomena you can check with your multimeter. Because typically the PN junction should not give a continuity beep in your multimeter. It should give only some value. If it is giving the beep, that means it is short. That means the junction is damaged. So we are talking about such kind of damage here, the junction burnout. Now next point is the oxide punch through is the other major category of the ESD damage. Oxide punch through occurs when an oxide is subjected to ESD pulse of high enough magnitude that can cause the oxide to break down. That means we talked about the percussion path through the oxide. That event will happen and damage the oxide, whether it is the gate oxide or some other oxide. Transient domain of an ESD event, the voltage applied the gate oxide must be very large to initiate oxide breakdown. So here we talk that the gate oxide must be very large to initiate the oxide breakdown. The voltage should be high. So in ESD, that is the voltage is very high and that breaks down the oxide. Metallization burnout is often a secondary effect occurring after the initial junction or the oxide failure take place. So metallization burnout means for the different contacts inside the IC, we have metallization there, metallization contact there. So that can even get metal contact can get burnout. So the metallization burnout occurs if the current flowing through the metal forces temperature to rise due to the I²R calculation high enough to reach the melting point of the metal. Three types of ESD damage we have talked about that can happen inside the chip. That is a junction burnout. The next one is the oxide punch through, and next one is the metallization burnout. So these are existing inside the IC, and this type of damages 1, 2 or 3 can happen due to the ESD. So here we are done talking about the various type of ESD damages that can happen inside a IC. Let's move on to the next slide. Characteristics of good ESD protector. So here in this slide we will talk about what the criterions a good ESD protector could have. That means whatever we are incorporating inside the IC, the characteristics that protection element should bear. The good ESD protection element should have the clamp ESD voltage to shunt the ESD stress count. Good ESD protection element should clamp the ESD voltage to shunt the ESD stress current. Next, it can turn on fast enough. That means there should be no delay so that it can act as a passage rather than if the ESD path keeps this particular element and goes to some other part, it can damage that other part. So this part, whatever protector we are using, that should turn on fast enough. Next, can carry large current. So it should have a high current carrying capability. Next, should have very low turn on resistance and minimum series resistance. So the resistance overall, whether it is a turn on resistance or the series resistance, that should be very, very low. It should occupy minimum area at the bond pad. There are pads we have talked about, right, in the IC fabrication. So it should occupy minimum area there. It should have minimum capacitance. So the capacitance should be minimum. Stand out robust against the numerous pulses. Not only one pulse. If multiple pulse of the ESD coming inside, it should be able to handle all those pulse, or rather it should able to handle the pulse train for the ESD. And finally, it should not interfere with the IC's function or the testing of the IC. That means the functional testing. This should be the typical criteria, a good ESD protection element that is getting incorporated inside your chip that should have. So here we are done. Let's move on to the next slide. ESD protection in VLSI design. Here we talk about the different VLSI steps that we do. First we start here the ESD design rules. So generally we have a physical verification stage where we check the design rules. There we incorporate the ESD design rules comes as with the ESD document. The protection design implementation becomes complicated for various IO signal configuration. Also, placement of unrelated circuits near an IO pad causes unexpected current paths through interaction or may render protection device ineffective. So these are checks that should be done by the designer, and the rules may have some of them incorporated. The same could occur in the internal connection between power supplies, preventing the power supply clamp from operating. All of these issues are covered in ESD design documents so that the product ESD design is addressed properly from the very beginning. All these things should be covered either manually or should be through the rules, the design rules. Whatever DRC engine that you are using, that should be able to check these things. ESD protection is done using several types of IO cells such as digital IO buffers, provide high drive up level shifting output, provide down level shifting and ESD protection for input. So digital IO buffers are there to protect from ESD, and also we have analog IO cells, provide ESD protected analog input out. Two different kind of circuits we generally have, digital and analog, and for both of them we have different type of ESD protection elements in VLSI. So here we are done for our basic VLSI checking step that is there in the VLSI design flow in the design rule check part, and there we check for the electrostatic discharge checking design rules. We're done here with this particular slide. Let's move on to the next slide. ESD protection methodology. The main goal of ESD protection circuits is to provide a low resistive discharge path. We have talked about in the criterion of a good ESD protector. So this we have already talked about. Now here is our typical drawing of various ESD protection unit. Here we are using the clamp. Earlier there was diode, and here is the clamp between the power rails. And this is our pad, an IO pad, VSS pad and VDD pad, and these are our power rails. Figure shows the typical chip level ESD protection scheme in which an ESD power supply clamp is connected between two power rails under the different faces. So this is ESD clamp, this is ESD clamp, this is for the VSS and this is for the VDD. We have different type of clamps connected different elsewhere. We'll go in detail, but however this is just for your FYI purpose. The ESD clamp provides the discharge path for an ESD event that happens between two power rails. So here is a spelling mistake, it is happens, not happens. Clamps should be of category of static clamps and transient clamps. Clamps could be two kind of different type of circuit operation. One is a static, another is the transient, based on the nature of the operation. The static ESD clamps turn on once the voltage across the supply rails exceed triggering voltage and start conducting the current of an ESD event. So this is the static, and it detects the two rails and accordingly it acts. The transient ESD clamp take advantage of the rapid change in the voltage during an ESD event to trigger the clamp using a rise time detector and a delay element to keep the clamping element on during the entire ESD event which is happening. So the static clamp acts in a different way and the transient clamp acts in a different way. Transient clamps acts during a circuit operation and the static one acts based on the power rails, the voltages in the power rails. If there is a danger level, it starts acting, and in the transient, during the transient operation, if there is a danger level, it acts at that point. Transient clamps are able to react fast. However, these circuits must be carefully designed to keep their leakage to minimum. So this is another design need because most of the devices now handle and battery operated. So the leakage should be minimum. That is our expectation. So here we talked about the ESD protection methodology, specifically static clamps and transient clamps we have talked about here. Let's move on to the next slide. ESD protection scheme diodes. Turn-on type device, that is the Zener diode. A turn-on type device like a Zener diode turns on after reaching a particular triggering voltage. Once the device is turned on, it offers a low impedance path for the ESD current to flow. The current voltage characteristics for such a device is shown in figure. So this is your typical Zener operation forward bias. Here we are not talking about the forward bias. We are focusing on the reverse bias, and you can see if we draw a perpendicular, right here we draw a perpendicular at this particular VZ. We generally this as VZ. At that particular VZ, that breakdown will happen, right? At this point, it will offer a path where huge amount of current can pass on. So you can see I is here, minus I is here, and this type of protection scheme can be used in a typical ESD protection layer where the level is characterized by VZ of the Zener diode. So you know, right? Even in our analog circuitry, different Zener diodes are available with different voltages. So VZ is not a fixed one or not a fixed value. It can be varying according to circuit design. Such Zener diodes could be placed and they can act as a ESD protector. So here how we place the Zener diode, we place like the diodes are shown here in between the pads, right? The VDD pad, IO pad and the VSS pad. One is connected towards the VDD and another one is connected towards the VSS. So this way we can place them. Diodes offer a simple and effective turn-on type ESD protection. They can be used either forward biased or reverse biased configuration since diode have IV characteristics as shown in the figure. So even if we have some requirements where this forward biased voltage is needed for that triggering voltage, we can also use that. So this is we mark it VI and this is VZ. So based on the need, we can either use in the forward biased VI voltage or VZ voltage depending upon whatever our circuit requirement is there. They offer a very low resistance path, you know, right? Whenever this is going high, this because here the voltage remains fixed and the current goes up, and here the same thing, here voltage remains fixed and the current goes high. Obviously in the negative I axis I'm talking about, hence it's a very low resistive path because the R is very less because the I shoots in here because this is a semiconductor. The advantages of this method, it can be simulated using the SPICE. So you can use your SPICE simulation program to check this kind of operation. One limitation is that the fixed diode turn-on voltage which can reduce the application of the diode for this. We have a limitation that we can use fixed level of voltage. I have just talked about based on the design you have to give a fixed voltage. If you are using the forward voltage here or you are using the reverse voltage here, whatever, this is fixed. You cannot change it. It's not dynamic. It's very static. This is the limitation. So here we have talked about diodes. We are done here. Let's move on to the next slide. Stacked diodes. So here we will talk about the next level of application of the diodes. That is, figure shows an ESD protection structure consisting of stacked diodes. So here you can see instead of single diode, we can stack diodes for our better protection. So this can be used. Under normal operating condition, diodes are reverse biased and hence in the off state. During an ESD event, the diode forward bias and divert the ESD induced current away from the internal circuit. The drawbacks of such structure include the relatively large on-state resistance and added complexity in optimizing the interconnect metallization parasitic for advanced CMOS process technology. So this is the drawback here we talked about in the fourth point. However, we can use stacked diode instead of single diode. In that, what will happen? So the voltages will be getting added. So VI or VZ, whatever is there, it will get added and accordingly the voltage will change. So this is the thing that we can also use stacked diodes. In some cases of the VLSI, the stacked diodes are also used. So we are done talking here. Let's move on to the next slide. ESD protection schemes, the snapback devices. Snapback type device. So the snapback type protection schemes are capable of handling very high current. So here you can see we have a SCR put here, a PNPN structure here. Rest of the circuit looks very familiar to you. We already talked about. We have two diodes here and we have a SCR here. And rest of the circuit is V8 VDD pad, IO pad, VSS pad and our power clamp. And this is the core of our circuit. Everything remains same. But here we are using a SCR here. You can see PNPN structure. Gate grounded NMOS, GGNMOS and gate coupled NMOS, GCNMOS and SCR, that is silicon control rectifier, are ESD protection devices which work based on the snapback mechanism. So in the SCR slide we show you the graph that whatever snapback means. Now let us see what type of SCRs are used here. 5 different types of SCR are used for ESD protection. Low voltage triggered SCR, that is LVT SCR. Gate coupled LVT SCR. So we have another type of LVT SCR here. Substrate triggered SCR, that is ST SCR. We have double triggered SCR, DT SCR. And we have boundary MOS triggered SCR. So all these type of SCRs can be used in your ESD protection type. So you can see the ESD protection itself is a very big science here that we apply as a technology in our VLSI technology. So here we are done with this particular slide. Let's move on to the next slide. Silicon control rectifier. So let us talk about the SCR here, whatever property of SCR we are dealing with and how it is getting used as a ESD protector. SCR which provides high value of area gain factor compared to other protection structures. So here you can see the IV characteristics. Here is the voltage and here is the current, and you can see the graph goes like this, and on certain point Vs the control snaps back to this point and it goes in a very high value current. So that means the voltage actually drops and then the current goes high. So here it gives a path for the current to pass on at a lower voltage, and it's almost here we have like this, but in actual practice you can see this will be almost a line parallel to this current I axis, the current axis. Here is the kind of representation of the PNPN SCR structure, that is PNPN. We have anode and cathode and gate here, and here is the BJT equivalent of this circuit. In theory, we also deal with the BJT equivalence, and that's why I have just given this particular schematic here, although it is not very important right now for our discussion, but just for your knowledge, we have posted it here. SCR is commonly used for ESD protection in advanced process technology. However, a SCR has triggering voltage of approximately 20 volt compared to low holding voltage like 1 to 2 volt. This volt is 1 to 2 volt and this is around 20 volt. So this is triggering happens at 20 volt and it snaps back and the voltage goes back to here and it's 1 to 2 volt and high current flows. So this is the beauty of SCR. SCR is popular for its area efficiency. With the same ESD protection level, SCR occupies smallest area among 3 basic devices. The area efficiency for SCR is very good, and that is we need because in VLSI we need the power, performance and area optimization. So we have an entire episode on PPA. You can go ahead and watch that. And also we have talked detail of the SCR operation in the Latchup episode. I have provided the links of these 2 videos in the description. You can go ahead and watch in case you have some interest on. The cross schematic view and the equivalent circuit of the SCR is shown in the figure, in which the consisting PNPN structure. After trigger, the SCR will exhibit snapback IV characteristics as shown. So here we have shown after the triggering, right? Triggering happens at that point and then it snaps back and the current goes high. This you can see this happens actually during the SCR operation acting as a ESD protector. Typically, SCR has large snapback. So that is what we told, right? 20 volt is a trigger and snapback voltage is 1 to 2 volt. So there is a large snapback here. Gate grounded NMOS, GGNMOS. To solve the ESD problem, GGNMOS, that is gate grounded NMOS, is commonly used for protection device. Here is the kind of schematic that we are using. Here you can see the GGNMOS, the NMOS is here. You can see the source drain is here, and you can see we have grounded the gate here. So this structure acts as a gate grounded NMOS. Rest of the circuit you are very familiar. We have displayed it couple of times from the beginning of this particular video. GGNMOS is easy to design and it is perfectly compatible with CMOS process. However, it consumes relatively large silicon area because of the low current driving capability. So this is the comparison to the SCR, where the area is efficient. Here the area is inefficient of the GGN-MOS. Although it is a snapback device, due to GGN-MOS has simple structure and it is compatible with the CMOS technology, it is also a popular device for ESD protection. GGN-MOS is modified form of the normal NMOS device, as we can see here from the schematic. In GGN-MOS, the drain of the NMOS serves as the anode and the shorted gate source and the body contact are tied together to serve as a cathode. This is the structure you can see from the schematics, and this is very simple to understand. We are done here. Let's move on to the next slide. ESD protection scheme. Now we talk about the different clamps. ESD protection circuit. There are different on-chip protection methods are used for ESD protection. The rail-based protection circuit is one of them. So rail-based means which is connected to the power rails directly. Placement of the power supply clamps determines the effectiveness of the IO protection of the rail-based ESD protection. So clamps are generally used for clamping purpose in between the rails, at least one of the rails. Here you can see this is the schematic of a VDD clamp, and here you can see that this is a schematic of a VSS clamp. So these are the two different circuits. So let me clean up and let me draw a line in between. So this one is VDD clamp that you can see it's connected with the VDD and also with that ground. For the VSS clamp, if we need for the VSS only, here the clamp is and this one is missing here. These are the two circuits. Power clamp. Power clamps are present inside each power supply IO. So you can see that pads are here and where the clamps are connected. Power clamps. Basically, we're talking about this, or this, not about this one. This is a power clamp. We're not talking about. They are used to shunt current to the ground from power supply lines when an ESD event occurs or any event which can potentially damage the electronic components. So we are talking about this because here as soon as if it is reaches right, this is the core of the circuit and this is clamp is for different purpose, but this will protect your chip, whatever things are coming from the pad. That means your human contact. The RC guard power clamp is a simple and efficient implementation of the archive of the same. We also have RC implemented power clamps also there. So these are the power clamps we have talked about. There are two type of schemes are there, VDD clamp and the VSS clamp. We have shown both schematics here. And so far we have discussed so many things on the ESD today in this episode. So we are done here with this particular slide. Let's move on to the next slide. Hey guys, welcome back to the computer screen, and in today's episode we are going to discuss the below points. Vertical cross section of a chip touch basing the FEOL, MEOL and BEOL layers, antenna phenomenon and its infographics. Next, we will cover the semiconductor CMOS process and the various plasma processes that are being used. Next, we will go through our antenna damage action replay and infographics to understand the damaging process. Next, we will cover the physics happening behind the antenna phenomenon and we will explain a ratio which is called the antenna ratio, closely related to the physics happening behind. Next, we will talk about the present VLSI methods of antenna issue mitigation and some infographics to understand the mitigation methods. That's the menu for today, and without any further delay, let's begin. Vertical cross section of a chip. So here we are using the vertical cross section of a chip. This picture has been taken from Wikipedia. Here I will point out the different layers. First one is the FEOL layer. Here the transistors will reside. Next, there are few other layer components which are very closely spaced with the FEOL like contacts, etc. Those are called the MEOL layer. And the entire metal routing process through metal and via stack are under the BEOL layers. Now, the reason of keeping this slide is to make an impression in your mind about the different layers starting from the silicon surface reaching up to the maximum metal layers. Shortly, you will understand the importance of this slide in upcoming slides. We're done with this particular slide, so let's move on to the next slide. What is antenna effect phenomenon? At present, chemical etching has been completely replaced by hot plasma etching. Plasma-related processes are used for CMOS process flow for etching and deposition. The gaseous plasma contains charged particles inside. This charge gets transferred to the under construction floating metal routes, which may be connected way below up to the gate areas of a MOSFET. At the same time, such metals may not be connected to any diffusion areas in the FEOL zone. Such metal wires act as antennas, that is, charge receptors that pick up electrical charge from the plasma gas. So in this line, you understand the meaning of the word antenna, because here the metal route is acting as an antenna to pick up charge from the plasma environment. Charge accumulation on the metal strip is proportional to its length. That means the larger the metal area or the length is bigger, the more the charge gets accumulated onto it. So here we are done with the short and sweet description of the antenna effect phenomenon. Let us move on to the next slide. Antenna phenomenon infographics. Here we will take the help of our infographics to understand the phenomena during the fabrication process. Here is our silicon substrate, source, drain. Here is our shallow trench isolation. Gate oxide is grown here. On top of that, poly is grown and connected to the metal 1. And after the metal 1 deposition, we have to etch the metal 1 as per the mask. So the plasma is coming down from the plasma chamber on top of the metal 1 for the etching process. And in this gaseous environment, many charge are getting accumulated on the metal 1 surface. Once this amount of charge is sufficiently high, it causes a breakdown of the gate oxide insulator and the charges pass on the silicon. This infographics helps you to understand the antenna phenomenon happening live during a CMOS process. We're done with this particular slide, so let's move on. What is antenna effect phenomenon? We will go through some more points to dig deeper inside the antenna effect phenomenon. Aforementioned metal wires built up high potential difference on the metal side through the piled up charge. As a consequence, high electric field builds up across the gate oxide of the metal oxide semiconductor, that is MOS structure of a MOSFET. Sufficient amount of charge creates a percussion path to the oxide for the drainage of the charge. This percussion path is a small path that is created by high amount of charge, and this is just a beginning. Severe drainage lead to the gate oxide breakdown, consequently damaging the MOSFET. Alternatively, in less severe drainage, non-damaged MOSFETs, hot electron generation, abbreviated as HCI, may take place, causing faster aging related to the performance degradation of the MOSFET. Yes, those MOSFETs which are not getting damaged during the application process due to the antenna phenomenon, even here a percussion path may be existing there where low amount of charge is getting accumulated, and these are causing the hot electrons gathered in the oxide, causing the aging. That means performance degradation of the MOSFET in the long run. We are done with this particular slide. Let's move on to the next slide. Now, in this slide, we will talk about the semiconductors. It's a brief walkthrough of the CMOS process. So here is a infographics. So first we do the deposition, then we use a photoresistive coating, we use the exposure, developing, etching. I have kept a green highlight here to make it separate from any other steps. Then there will be ion implantation, and then there will be the stripping of the remaining mask. So this is a cyclic process. It keeps on operating for formation of the metal routes in the BUL region I have shown in the first slide. The FUL and MUL obviously go through this process. However, the BUL goes through this cyclic process several times, and the step marked in green, etching, is the process step where we are using the plasma, and here the chances of getting the antennas. Don't think that antenna violation is happening to only metal 1. It can happen in any of the metal layers as shown in the picture where I have marked the BUL layers. We're done with this particular slide, so let's move on to the next slide. Different types of plasma process. Now this is going a bit deep in the semiconductor CMOS process. Here we will talk about 3 different plasma process, and that will enhance your knowledge about how the plasma process is done and what is the respective importance, and we will correlate these things to the antenna damage later on. Conductor layer pattern etching process. Here the amount of accumulated charge is proportional to the perimeter length of the conducting metal stripping above. Etching process splits the conductor layer plates into multiple routing patterns. Perimeters of the pleated routing are directly exposed to plasma. Here we have just touched based one particular type of plasma process. Next, etching process. Here, the amount of accumulated charge is proportional to the area of the conductor layer pattern. Etching process, remove remaining photoresist layers after etching processes of a conductor layer. Area of conductor layer pattern is directly exposed to plasma. Can you spot the difference? In the first one, the perimeter was exposed to plasma. Here, the area is exposed to plasma. Next, contact etching process. Here the amount of accumulated charge is proportional to the area of the total area of the contacts. Contact etching process dig holes between two conductor layers. That means we have metal 1, metal 2 stack, right? We have to dig a hole through it to make the via, right? So there is particular etching process is used. Here the area of all the contacts on the lower conductor layer pattern is directly exposed to the plasma. Now you are familiar with the three different plasma processes that are used in the semiconductor CMOS processing, and in this particular process steps, the plasma affects the metal layers and may create the antenna problem in different ways. We are done with this particular slide. Let's move on to the next slide. Antenna damage action replay. Metal or via stacks are built layer by layer. First, metal 1 is deposited and all unwanted portions are etched away by the plasma etching. Then the metal geometries, when they are exposed to plasma, can collect the charge from it. So at this point, you may recall the three different type of plasma exposure that I have just talked about in the last slide. Once metal 1 is completed, via 1 is built, and then metal 2 and so on. So with passing stage, the metal geometries can build up static electricity. If the charge collected is large enough to cause the current to flow to the gate, this can cause the damage to the gate oxide. Long metal lines are prone to such failures, ending into fabrication yield. That means if the antenna damage happens, the chips that are coming out of a batch, huge amount of chips will be defunct. So those chips which has gone through the antenna damage, those will be non-functional. That means we have a higher yield entire fabrication batch. So we are done with this particular slide. Let's move on to the next slide. Action replay infographics. Here is our expectation. Here we'll go through the expectation in a semiconductor process. Ideally, that should happen. Here is our diffusion layer, and here is our gate oxide and poly from a MOSFET. Here we are reaching up to M1, and here also we are reaching up to M1. Then we are reaching up to M2, which is connecting the diffusion zone up to the gate area. So this is a kind of wiring that is inside the circuit, and we expect this thing to happen as shown in the picture through the various process masks in the semiconductor fabrication process. What we have there in the reality, diffusion layer is here. Here is the poly and gate oxide. You can compare the two things. Here we are reaching up to metal 1. Then here, the plasma induced charge accumulation happens on metal 1, which may cause the breakdown of the gate oxide. Here is the plasma environment, and here goes the breakdown once all charges which have accumulated exceeds a certain limit. So this is the real. So this way you can understand various different connection inside the fabrication process go through. So even before reaching the realistic process step, where in the above picture you can see the M2 is connecting. In the M1 etching step, the plasma induced charge, also known as the antenna phenomenon, happens and it damages the gate oxide from the right hand side. This is a realistic action replay, means whatever we expect ideally and what happens in actual world. We are done with these infographics. Let's move on to the physics happening behind. Non-uniform density of plasma across the wafer plays an important role in antenna related damage. Remember, here we'll go deep into the physics happening in the antenna phenomenon. Such non-uniformity can come from non-uniformity in radio frequency, RF current flow, electron current flow, ion current flow. All these are related when a semiconductor process is going. In addition to this, the electron shading effect can contribute plasma charge. What is the electron shading? The plasma charging, that is metal, and discharging through oxide can severely degrade or destroy devices, especially metal oxide semiconductor, that is MOS gate dielectric. This particular problem is becoming more prominent in lower technology node with the thinner gate oxide. The gate oxide degradation occurs by the physics, that is the Fowler-Norden FN tunneling phenomena between the gate oxide and the silicon substrate. That means gate oxide, which is residing between the gate and the silicon substrate, goes through Fowler-Norden tunneling phenomena, and that starts the charge passing, creation of the percussion path, and finally when there is huge amount of charge flux is going through the oxide. In the continuous plasma exposure environment, the gate potential builds up, adjusts itself by the FN tunneling current. The flow of the tunneling current generates trap and interface states in the gate oxide, gradually degrading the oxide quality and integrity. At very high level of stress or prolonged exposure also ultimately lead to the breakdown of the oxide. In high aspect ratio spaces, isotropic electrons are hindered from reaching out the bottom of the space, whereas anisotropic and positively charged ions are not. This phenomenon is called the electron shading that I have just mentioned in the previous slide, which happens in the uniform plasma when topography exists on the wafer during the plasma exposure. Insulators such as photoresist or oxides are commonly used as masks when etching conductive films. The underlying conductor can acquire a positive charge by the electron shading mechanism. This way, I have pointed out all the physics that is happening behind the scene of the antenna breakdown in 2 consecutive slides. They are done here. Let's move on to the next. Antenna ratio. So this antenna ratio is a very important point, and you may get this ratio from your design rule manual, and it is very important for your antenna analysis. The magnitude of the accumulated charge depends on the ratio of the floating conducting region area to the gate area. This is called the antenna ratio and quoted in design rule manual. So the antenna ratio is equal to the total exposed antenna area divided by total gate oxide area. It can be equated with the current densities JFN function of VG and JP that is function of VG. Now what are these? VG is the gate voltage on all the gate oxides connected to a particular wire segment, which is under the antenna effect consideration. The charging current density JP is a function of the antenna voltage and the tunneling current density. JFN is a function of the gate voltage when the technology parameters are kept constant. The above equation shows the relationship between the antenna ratio and the current density. A higher antenna ratio means a larger VG, thus a larger JFN and more damage. This ratio very important with respect to the physics happening behind the antenna breakdown. So we're done with this particular slide. Let's move on to the next slide. Antenna issue mitigation. There are few ways to eliminate the antenna effect. Jumper insertion. This is creating a metal bridge, also known as jumper, near the gate of the MOS device, so that this is creating a metal bridge, also known as jumper, near the gate of a MOS device while fabrication. This jumper could take gate connections directly up to the top level metal through stacked vias. Here we are talking about the jumper creation in the BOL section. BOL section you can remember from the first slide. Consequently, the gate will not see any antenna due to the breakup of a long metal piece into stacked metal or via layers. The drawback of the use of stacked vias can lead to routing congestion and hence also the increase in die area. Stacked metal or vias may or may not lead to EM or IR reliability issues. Antenna issue mitigation. We continue here with few more points or few more ways of mitigating the antenna phenomenon. Gate protection diode. Here we connect each gate to reverse bias PN diodes. Using diode provides a discharge path directly to the substrate by contact to a diffusion area. If possible, these diodes are connected to gate with metal 1 so that prevention starts right with metal 1 fabrication. During normal operation, this reverse bias diode will not affect the functionality. However, the plasma-induced charge is discharged through the diodes, leaving the gate unaffected. Drawback is the usage of antenna diodes may increase the die area by 4 to 6%. So we are done with this slide. Let's move on to the next slide. Here we will be showing the antenna mitigation infographics to understand the mitigation process in a more visual manner. Here we will demonstrate the jumper creation. Here is our diffusion. Here is our poly and gate oxide combination of a MOS, and here we are reaching to M1, and then here we are breaking down the long M1 on the right hand side. This we have already shown in few slides back, you recall, and connect the M2 here while we connect the jumper here. So you can see the right hand side long metal piece of M1 is broken and taken through a jumper. Now this jumper connection is a simple connection shown. However, in reality this may spread very high in the BOL stack. Next, here we have the diffusion, and we are showing here the diode method, and here is our poly and gate oxide combination, MOS, that is MOS structure. Here we can think there is a MOSFET, and here we are reaching up to M1. Here we are using the M2, and you can see we are dropping the diode here. So this is the diode method. Antenna issue mitigation. Here we will proceed with 2 more mitigation techniques. Embedded protection diode. Add protection diodes on every input port of every standard cell. Here we are using a precautionary diode. These diodes are embedded and fixed. Hence, these consume unnecessary area. Diode insertion after PNR. Fixing only the wire with antenna violation, which will not waste routing resources. During wafer manufacturing, all the inserted diodes are floating or ground. One diode can be used to protect all input ports that are connected to the same output ports. So here we talk about the embedded protection diode method and diode insertion after PNR. We are done with this particular slide. Let's move on to the next slide. Here we will show the infographics of the discussed methods here. So here is our silicon substrate, and it is our STI, source, drain, gate oxide, poly, source, drain, gate oxide, poly, and here we are reaching up to the metal 1, and then we are reaching up to the metal 2, and finally we are reaching up P, and the stack goes on in the POL zone, and here we are reaching up to the M4. So this is a typical connection that is shown to you, and the right hand side MOS and the left hand side MOS belongs to 2 different standard cells. Now here what we do, as we have just discussed in the last slide, we keep embedded diodes per cell. That means for left hand cell there will be 1 diode, and the right hand side there will be 1 diode. So here goes our diode. Here goes our diode. So this diode and this diode are the pre-existing diodes that will take care of the antenna issues, and these are included in the right hand side standard cell as well as in the left hand side standard cell. So this way, pre-existing diodes, that means the diodes which take care of the antenna issue, are included during the standard cell. So here we are done with this particular infographics. Let's move on to the next slide. Here we'll go through another infographics. Here is our routing obstacles, and you can see that diode insertion prohibited area. So here we cannot do the insertion of the diode, and here we have routing obstacle. So you can see the layout here, and here also we have the routing obstacle. Now in this scenario, we have to include some antenna diode. What we will do? We'll proceed like this. Here you can see some changes if you compare the left hand side picture with the right hand side picture, and here are the diodes which are inserted PNR level. These are antenna diodes inserted during the PNR or after the PNR level, and this way we covered the 2 infographics of the discussed antenna mitigation method. So you're done with the particular slide. Let's move on to the next slide. Thank you very much for watching up to this point, and don't forget to like, share and subscribe in case you have some dislikes. Put that as in words in the comment section down below, and bye for today.